Hello there, and welcome once again to Science for Sleep, where curiosity slows its steps and science takes a gentler tone, inviting you to rest while you listen. Tonight we're going to explore something immense, something that almost feels too large to hold in our minds. It's a question as old as the first people who looked up at the night sky and wondered what truly makes the universe run. What is the most powerful thing in existence? It might seem like an impossible question, because power can mean many different things depending on how you measure it. For some, it might be the blazing light of a star, the crushing pull of gravity, or the silent push of dark energy. For others, it could be something even smaller and harder to imagine, like the interactions of quantum fields. But before we dive into those possibilities, let me ask you something simple, and maybe even personal. Where are you right now as you listen to this? Are you lying in bed, ready to drift off, or are you tucked into a favourite chair, winding down after a long day? The universe feels vast and distant, but you are part of it, breathing within it, carried along by the same forces that move galaxies. And that connection is what makes the question of power so fascinating. It's a comforting thought to remember that the same laws that describe the collapse of a star also describe the falling of an apple, or the way your body rests against the mattress beneath you. Power isn't only about overwhelming strength. In physics, power has a specific meaning. It's the rate at which energy is transferred, transformed, or used. Energy itself is the ability to do work, and power is how quickly that energy is applied. You might think of a light bulb. The brightness of the bulb depends on how much electrical energy it consumes per second. That number is its power rating, written in watts. A small bulb might use only a few watts, while the sun outputs about 3.8 times 10 to the power of 26 watts, a figure so large it's difficult to imagine, and yet even that, enormous as it is, might not be the most powerful thing in the universe. The scale we're dealing with tonight stretches far beyond human experience. On Earth, the most powerful machines we've built, like particle accelerators, nuclear plants, and rockets, deal with power in the billions or trillions of watts. Impressive compared to everyday appliances, but minuscule next to the events playing out across the cosmos. A single supernova, the explosion of a massive star, can outshine an entire galaxy for a short time. The power released in those moments is staggering, but still it may not be the ultimate. When scientists ask what the most powerful thing in the universe is, they're not just comparing explosions or beams of light. They're asking about fundamental forces, about the mechanisms that hold matter together or tear it apart, about the engines that shape everything from atoms to galaxies. Before we dive deeper into this, I want to pause with you and just consider the scale of what we're dealing with. The universe is estimated to be around 13.8 billion years old. In that time, countless stars have lived and died, galaxies have formed and collided, and black holes have swallowed entire suns. Every second, somewhere, unimaginable amounts of energy are being released. Yet here you are, a tiny observer in the middle of it all, with a brain capable of wondering, asking questions, and imagining what power really means. If you find this journey soothing or even a helpful way to drift into rest, I'd be grateful if you gave the video a like, or maybe subscribed, so this little corner of calm can reach others who might need a place to unwind as well. So, when we ask about the most powerful thing in the universe, we're stepping into a puzzle. Do we mean the strongest force, the largest energy release, the most dominant influence shaping the cosmos? Each angle gives us a different candidate. Gravity, for example, is the weakest of the four fundamental forces when measured between particles. A proton and an electron attract each other gravitationally, but that attraction is about 10 to the power of 39 times weaker than the electric force between them. Yet gravity also builds stars, governs planets, and sculpts galaxies, weak individually, overwhelming in total effect. Electromagnetism is much stronger and controls chemistry, light, and technology. The strong nuclear force is even more intense, gluing atomic nuclei together. Without it, atoms would fly apart. The weak force, less obvious but equally essential, enables nuclear reactions that power the stars. Already we see that the word powerful can't be answered with a single simple statement. It depends on context. Imagine holding a small magnet in your hand and using it to lift a paperclip. With almost no effort, you've overcome the gravitational pull of the entire Earth on that tiny piece of metal. Electromagnetism has shown its strength in a very ordinary way. But when a star collapses under its own gravity and becomes a black hole, gravity reveals its strength on an entirely different level. Power lies not only in intensity but in reach and consequence. This is why our exploration must take us across many different scales. From the smallest particles to the largest cosmic structures, each has its own claim to being the most powerful. To prepare for that, let's get comfortable with what we mean when we talk about energy and power in physics. Energy exists in many forms: kinetic energy, potential energy, thermal energy, electromagnetic radiation, and more. Each can transform into another. A falling rock converts gravitational potential energy into kinetic energy. A light bulb turns electrical energy into light and heat. A star fuses hydrogen into helium, releasing nuclear energy as light and radiation. Power is about how fast these transformations happen. An earthquake releases a huge amount of energy, but spread over minutes or hours, its power is less than a supernova that releases vastly more energy in just seconds. It's worth noting that the most powerful events in the universe aren't just impressive in numbers, they're essential to existence. Supernovae scatter heavy elements like carbon, oxygen, and iron into space, seeding future stars and planets. Without these explosions, there would be no planets, no chemistry of life, no people to wonder about power. Black holes, while destructive in appearance, may regulate galaxy formation by spewing jets of energy that influence starbirth. Dark energy, though mysterious, is the reason the universe's expansion is accelerating, shaping the ultimate fate of everything. So power is not just a matter of raw might. It's about shaping, influencing, and sustaining the cosmos. Let's consider an example close to home: the Sun. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. In the process, about 4 million tons of matter are converted directly into energy, thanks to Einstein's famous equation E equals mc squared. That energy radiates outward, travelling through space, and a tiny fraction of it reaches Earth, sustaining life, driving weather, and powering ecosystems. The Sun outputs 3.8 times 10 to the 26th watts continuously. If you tried to match that with human technology, you would need billions upon billions of power plants. And yet, the Sun is an average star, not particularly large or bright compared to others. Some stars are thousands of times more luminous. Others end their lives in explosions that briefly outshine entire galaxies. The scale keeps growing the further we look. But even beyond stars, the question expands. When two neutron stars collide, the energy released in gravitational waves and gamma-ray bursts can exceed anything a supernova produces. When galaxies merge, the combined motions and interactions release unimaginable amounts of kinetic and gravitational energy. And when we think about the universe as a whole, with dark energy accelerating its expansion, we're talking about a force that dominates everything at the largest scales, even though it remains one of the greatest mysteries of physics. The question of what is most powerful is really an invitation to explore all of these phenomena, one by one, and to see how they fit together. Some forces dominate at small scales, holding matter together. Others rule the large-scale structure of the cosmos. Some bursts of energy are brief but intense. Others are steady and continuous across billions of years. None of them tells the whole story alone. But by examining each, we'll begin to see why scientists are still debating what truly deserves the title of most powerful. As you listen, notice how the ideas connect. The nuclear forces explain the structure of matter. Electromagnetism shapes chemistry and light. Gravity builds stars and galaxies. dark energy drives cosmic expansion. Each has its role, and each competes in its own way for that title. When we talk about power tonight, it's not only about numbers on a chart, though we'll mention plenty. It's about understanding the role each kind of power plays in the grand design of the universe. And in that sense, our journey will be both scientific and quietly human, because the very act of asking what is most powerful shows our curiosity, our drive to understand, and our place in this immense picture. When we talk about power in everyday life, we might think of influence, authority, or control. Someone powerful might be a leader, or an event might be described as powerful because it moves us deeply. But in physics, the word has a very particular meaning. Power is not about politics or emotions. It is about the rate at which energy is transferred, transformed, or used. That one word, rate, is what makes power such a distinct and fascinating measure. It tells us not only how much energy exists, but how quickly that energy changes form or moves from one place to another. Imagine holding a battery in your hand. Inside that battery is stored chemical energy. If you connect it to a small light bulb, it might glow faintly for many hours, using only a tiny amount of energy each second. That same battery could instead be used to deliver a strong but brief burst of energy in a device that needs it all at once. The total energy stored is the same, but the power, the speed at which that energy is delivered is very different. A glowing bulb and a sudden spark may both come from the same battery, yet one uses its energy slowly and the other quickly. This is why physicists separate energy and power. Energy is the capacity to do work. Power is how fast that capacity is spent or transferred. If energy is money, power is your spending rate. Two people might both have $100. One spends $10 a day and makes it last 10 days. The other spends $50 a day and runs out in 2 days. The total wealth is the same, but the power of their spending is very different. In physics, we measure power in watts. 1 watt is 1 joule of energy used or transferred each second. A joule itself is a small unit of energy. Lifting an apple about a meter against Earth's gravity takes roughly 1 joule of work. So if you lift 1 apple every second, you are working at 1 watt of power. A person climbing stairs, a car driving on a highway, a rocket launching into space, each of these can be described in terms of watts, showing how much energy flows per unit of time. Your body itself runs on power. At rest, an adult human requires around 100 watts just to stay alive, keeping cells functioning and organs working. That's about the same as an old incandescent light bulb glowing all day long. When you exercise hard, your body's power output can briefly rise to hundreds of watts, or even more. Professional cyclists in races like the Tour de France sometimes sustain 400 watts, or higher for extended periods. The energy ultimately comes from food, broken down by your cells, transformed into motion and heat. In that way, every living thing is a kind of power plant, converting chemical energy into biological work. Now compare that to the machines humans have built. A typical car engine might generate tens of thousands of watts, a jet engine, millions, a large power station on Earth, billions of watts, and yet all of these, impressive as they seem, are dwarfed by natural processes. A thunderstorm releases energy equivalent to billions of watts, a hurricane, trillions, and the sun, that steady presence in our sky, produces on the order of 3.8 times 10 to the power of 26 watts every single second. It is almost impossible to imagine. But when we start comparing these numbers, we need to be careful. Power can look different depending on the timescale. A nuclear bomb, for example, releases energy in a fraction of a second, so its power output is extraordinary during that brief flash. A star, on the other hand, sustains its output steadily for billions of years. Which one is more powerful? The bomb might have the higher peak power, but the star has the overwhelming endurance. In physics, this distinction matters. Some of the most powerful things in the universe are not violent bursts, but long, steady engines. This brings us back to definitions. Work, energy, and power are closely tied. Work in physics is the process of transferring energy through a force acting over a distance. If you push a box across the floor, you are doing work. The energy you use from your muscles is transferred into the box, into friction, into sound, and into heat. The amount of energy you've transferred is measured in joules. The rate at which you do it is power, measured in watts. The faster you push, the more watts you are outputting. Physicists often use equations to keep these ideas clear. Power is equal to energy divided by time. If you use 100 joules in 10 seconds, your power is 10 watts. If you use that same 100 joules in just 1 second, your power is 100 watts. The total energy is the same, but the rate is very different. This simple relationship lets us compare everything from light bulbs to supernovae on the same scale. Even the 4 fundamental forces of nature can be compared this way. When 2 charged particles interact through electromagnetism, the energy transfer happens at different rates depending on distance, motion, and charge. Gravity pulls objects together, releasing potential energy as they move. Nuclear forces operate within atoms, with enormous amounts of energy concentrated in tiny volumes, released in fractions of a second when atoms split or fuse. Each of these can be described in terms of how quickly energy is moved or changed. Let's make this more concrete. Think about lightning. A single bolt carries about 1 billion joules of energy. That sounds like an enormous amount, and it is enough to power a household for weeks. But the bolt happens in less than a second, which means its power is on the order of 1 billion watts or more during that moment. For comparison, a nuclear power plant producing electricity for a city might generate 1 billion watts as well, but continuously for years at a time. The same unit, watts, links the instant flash of lightning and the steady hum of a power station. Another striking example is the energy locked inside matter itself. Einstein's equation, E equals mc squared, tells us that mass and energy are interchangeable. A small amount of mass can become an enormous amount of energy because the speed of light squared is such a large number. 1 kilogram of matter, if completely converted, would yield about 90 trillion joules of energy. If that happened in a second, the power would be 90 trillion watts. This is why nuclear reactions are so powerful compared to chemical reactions. They tap into the deep binding energy of atomic nuclei, not just the bonds between atoms. This brings us closer to the idea of ultimate power in the universe. Because when we ask what is most powerful, we are really comparing rates. Which phenomena release the most energy per second? Which forces transform matter most rapidly? Which processes dominate across the cosmos, shaping everything else? Defining power carefully allows us to start answering these questions. Without that clarity, we might confuse steady energy output with brief bursts, or confuse local strength with universal influence. It's helpful to pause here and think about why power matters. For life on Earth, it matters because everything we do depends on a flow of energy. The warmth of the sun powers photosynthesis, which feeds plants, which feed animals, which feed us. The circulation of air and water, the growth of forests, the building of cities, all of it depends on power moving through systems. On a cosmic scale, galaxies form and evolve through the balance of power between gravity pulling inward and energy radiating outward. Even the ultimate fate of the universe may depend on which form of power dominates, gravity trying to slow expansion or dark energy pushing it faster. As we drift deeper into this thought, it becomes clear that power is not just a dry definition from a physics textbook. It is a lens through which we can see everything from the simplest movement of an apple falling to the most dramatic burst of gamma rays in the distant universe. It gives us a way to compare, to measure, and to understand phenomena that at first seem incomparable. When you flip a switch and a light turns on, you are controlling a tiny flow of power. When a star collapses into a black hole, power is released on a scale so vast it makes human technology seem like a whisper. yet both can be described with the same units, the same principles, the same definition. That is the elegance of physics. The definitions we start with here, energy, work, power, become the foundation for everything else we'll explore. When we speak about power in physics, we're always referring back to something deeper, something more fundamental that sits underneath. That foundation is energy. To understand what the most powerful thing in the universe might be, we have to first become comfortable with energy itself. Without it, the word power has no meaning at all. Energy is the thread that connects everything, from the smallest vibration of a particle to the largest galaxy clusters stretching across the observable universe. It is so central to physics that some call it the currency of the cosmos, the medium through which every transaction of change is made. Energy is not a mysterious substance floating in space. It is a measurable quantity, one that takes many forms. A moving object carries kinetic energy. A compressed spring, a rock on a cliff, or a stretched rubber band carries potential energy. Light itself carries energy as electromagnetic radiation. Inside atoms, there is nuclear binding energy holding protons and neutrons together. Even empty space is not truly empty, because quantum fields give rise to vacuum energy. And through it all, energy can change its form, but it never disappears. This is one of the most important principles in all of science, the law of conservation of energy. That law tells us that in a closed system, the total amount of energy remains constant. It can move from one place to another, transform from kinetic to thermal to electromagnetic, but the sum is always the same. When a ball rolls downhill, the potential energy it had at the top is converted into kinetic energy at the bottom. When you rub your hands together, the kinetic energy of motion becomes thermal energy, and you feel heat. When a star shines, nuclear binding energy is converted into light and particles that stream across space. Each transformation respects the conservation law. No matter how wild the process, the total energy before and after remains constant. It is worth pausing here because this idea is so simple yet so profound. Energy cannot be created or destroyed. It can only change form. That means every bit of energy you experience has been part of the universe since its beginning. The warmth you feel from sunlight was born in the core of the sun, but before that it was stored in hydrogen nuclei formed billions of years ago. The food you eat contains energy from plants, which captured sunlight, which came from nuclear fusion, which drew on the binding energy of protons and neutrons, which themselves are the products of ancient cosmic processes. Every calorie, every joule, is part of a chain stretching back to the birth of the cosmos. To make this less abstract, think about energy in your daily life. The food you eat contains chemical energy stored in molecular bonds. Your body breaks those bonds, releasing the energy to power muscle contractions, nerve signals, and cellular processes. When you walk, that energy becomes kinetic. When you climb stairs, some of it becomes gravitational potential energy. When you sit down afterward, your body still burns energy to keep warm, to keep your heart beating, to keep your brain active. Even when you are lying still, drifting into sleep, energy flows quietly inside you. On Earth, we harness energy in countless ways. Burning fossil fuels releases chemical energy. Wind turbines capture kinetic energy of moving air. Solar panels convert light into electricity. Nuclear plants draw on the binding energy of atomic nuclei. In each case, it is the same principle. Energy is transformed from one form to another, always following the rules, always conserved. The units we use may differ, but the concept is universal. A joule of energy is the same whether it is in the form of heat, motion, or light. Now imagine scaling this up to cosmic dimensions. A planet orbiting a star has gravitational potential energy in the way it is bound to that star. As it moves, that potential continually shifts into kinetic and back again, keeping the orbit stable. A comet falling inward from the edges of a solar system speeds up as potential becomes kinetic, then slows again as it climbs back outward, trading one form of energy for another. Galaxies colliding release enormous amounts of gravitational energy as stars and gas clouds interact. Black holes merging send out ripples of energy across space in the form of gravitational waves, tiny distortions of space-time itself carrying away power at rates that outshine all the stars in the observable universe combined. At the heart of all this is the recognition that energy is not just one thing, but many. It appears as light, heat, motion, mass, fields, and more. And yet it is always interchangeable. Einstein's equation, E equals mc squared, tells us that mass itself is a form of energy. That simple equation has reshaped how we see the universe. A tiny amount of mass can unleash staggering amounts of energy. This is what powers stars and fuels nuclear reactions. It also means that energy and matter are deeply connected. The universe is not divided into stuff and energy. Matter is energy, bound in a particular way. Energy is matter, transformed into radiation or particles. The two are facets of the same underlying reality. This leads us to wonder how much energy the universe truly contains. If you try to count it up, the numbers become overwhelming. The Sun, with its 3.8 times 10 to the 26 watts, is just one star among perhaps 200 billion in the Milky Way galaxy. Multiply that by the hundreds of billions of galaxies in the observable universe, and the total energy output at any moment is beyond comprehension. Yet even this luminous energy is only a fraction of the total. Most of the mass energy of the universe is in the form of dark matter and dark energy, mysterious components we cannot yet fully describe. Still, whatever their nature, they carry energy, and so they must be included in the balance sheet of the cosmos. Energy also gives us a way to understand the past and predict the future. The early universe, just moments after the Big Bang, was a sea of energy, extremely hot and dense. As it expanded, that energy spread out, cooling, condensing into matter, stars and galaxies. The cosmic microwave background we see today is the cooled remnant of that early fire, a faint glow of energy left over from the birth of everything. Looking forward, the fate of the universe may depend on the balance of energy forms. If dark energy continues to dominate, the expansion will accelerate forever, spreading energy thinner and thinner. If some other form takes over, the story may change. We sometimes speak casually about running out of energy, whether it is our own tiredness at the end of a day or concerns about fuel sources for civilization. In reality, the total energy of the universe does not diminish. What happens instead is that energy becomes less useful for doing work as it spreads out and increases in entropy. A hot cup of tea cools down as its energy disperses into the air, still present but no longer concentrated. Stars burn their fuel, releasing light and heat into space, eventually fading as their energy becomes diffuse. The universe overall is heading toward a state where energy is evenly spread, unable to create new structures or motion. This direction is set by the second law of thermodynamics, and it is why energy feels precious even though it is conserved. In thinking about the most powerful things in existence, we must therefore think carefully about energy. A gamma-ray burst might release more energy in seconds than the Sun does in its entire lifetime. A black hole merger may radiate away staggering amounts in gravitational waves. But the underlying measure is always energy transformed per unit time. That is why defining energy clearly and respecting its conservation is so important for our search. Without it, the word power would have no anchor. It is striking too that energy is something we can measure so precisely. The joule, the electron volt, the calorie. These units let us compare things as different as chemical reactions and cosmic explosions. They give us a common language, and yet behind that precision lies mystery. We still do not fully understand why the vacuum of space has the energy it does. We still do not know what dark energy truly is. We know that energy is conserved, but we do not know why the universe has exactly the amount it has. Some theories suggest the total energy of the universe might even be zero, with positive energy of matter balanced perfectly by negative energy of gravity. If that is true, then everything we see might be a kind of cosmic accounting trick, with creation and existence emerging from a balance sheet that always sums to nothing. But whether the total is zero or immense, energy is what makes the universe active, structured, and dynamic. It fuels every star, drives every galaxy, powers every heartbeat. It is the reason we can ask questions, the reason we can think, the reason we can rest. In physics, to speak of energy is to speak of possibility. Every change, every motion, every interaction is a story of energy moving, transforming, and persisting. And when we look for what is most powerful in the universe, energy is always at the heart of the answer. Gravity has a quiet persistence that can be easy to overlook in daily life. You notice it when you drop something, when you feel your body resting against the bed or the chair beneath you, or when you see the moon rising in the night sky. It does not flash with light like electricity, and it does not give off heat like fire. It has no colour or sound, and yet, without it, the universe as we know it could not exist. Stars would never have formed, planets would not orbit, and galaxies would not hold together. Gravity is the force that takes energy and matter and sculpts them into structure, pulling the scattered ingredients of the cosmos into patterns that endure. In physics, gravity is described as one of the 4 fundamental forces of nature, but it is also the most familiar to us. From the time you were very small, you knew instinctively that things fall downward. You may have learned the story of Isaac Newton watching an apple drop from a tree, an ordinary event that led to a profound realization. The same force that pulls an apple toward the ground is the one that keeps the moon in orbit around the Earth. The same equations that describe a tossed stone also describe the motion of planets around the sun. That insight was one of the great turning points in science, because it showed that the heavens and the earth obey the same laws. Newton described gravity as a force acting at a distance. Every object with mass attracts every other object with mass, and the strength of that attraction depends on their masses and the square of the distance between them. The more massive the objects, the stronger the pull. The farther apart they are, the weaker the pull becomes. With this formula, scientists could predict the orbits of planets with remarkable accuracy, calculate tides, and understand why comets trace long arcs across the sky. Gravity became a unifying principle, linking the fall of an apple to the dance of celestial bodies. Centuries later, Albert Einstein expanded this picture in an even more profound way. In his theory of general relativity, gravity is not a force transmitted across space. Instead, it is the curvature of space-time itself. Mass and energy bend the fabric of space-time, and objects move along the curves of that geometry. To visualize it, imagine placing a heavy ball on a stretched sheet. The sheet dips under the ball, and smaller objects placed nearby roll toward it, not because the ball is pulling directly on them, but because the surface is curved. In reality, space-time is 4-dimensional, and the analogy with a sheet is imperfect, but the idea captures the essence. Gravity is geometry, and mass tells space-time how to curve, while space-time tells mass how to move. This description has been tested in countless ways. Light bends around massive objects as observed during solar eclipses. Clocks run more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. Ripples in space-time, called gravitational waves, have been directly detected from the collisions of black holes and neutron stars. Each of these observations confirms that gravity is not only real, but it is precisely as Einstein described it, a dynamic curvature shaping the cosmos. What makes gravity remarkable is that, compared to the other fundamental forces, it is incredibly weak. If you pick up a paperclip with a small magnet, the electromagnetic force between the magnet and the paperclip is strong enough to overcome the gravitational pull of the entire Earth on that piece of metal. The strong nuclear force that binds protons and neutrons inside nuclei is about 10 to the 38th power times stronger than gravity. The electromagnetic force is about 10 to the 36 power times stronger. Even the weak nuclear force, often overshadowed, is still vastly stronger than gravity at the scale of individual particles, and yet gravity dominates the universe at large scales. The reason is that it always attracts, and it has infinite range. Positive and negative electric charges can cancel out, leaving objects electrically neutral. Nuclear forces are confined within atoms and vanish at larger distances, but gravity never cancels. Every bit of mass adds to every other bit. Over vast distances, even a small attraction accumulates. Given enough matter, gravity takes over, pulling clouds of gas into stars, holding stars into galaxies and binding galaxies into clusters. Weak locally, overwhelming globally. You can see this hierarchy in the night sky. Stars exist because gravity pulled together clouds of hydrogen and helium until pressure and temperature grew high enough to ignite nuclear fusion. Planets orbit stars because gravity shapes their paths. Moons circle planets for the same reason. Our own Earth holds an atmosphere because gravity keeps gases from drifting into space. It raises tides through the moon's pull, and it maintains the balance of orbits in the solar system. At every level, gravity sets the architecture. Consider galaxies. A galaxy like the Milky Way contains hundreds of billions of stars, each one moving in orbit around the galactic center. What holds them together? Gravity. Without it, the stars would drift apart, and the galaxy would dissolve. Galaxy clusters, the largest gravitationally bound structures in the universe, contain thousands of galaxies, and their stability comes from the combined gravity of visible matter and dark matter. Gravity is the great collector, the organizer of cosmic structure. Even more astonishing are black holes, places where gravity is so intense that not even light can escape. Formed from the collapse of massive stars or the merging of smaller black holes, they represent the extreme edge of gravitational physics. At their centers lies a singularity, a point where density becomes infinite and our current theories break down. Around them, space curves so steeply that time itself slows. At the boundary known as the event horizon, the escape velocity exceeds the speed of light. Black holes demonstrate gravity at its most extreme, warping space-time into configurations that challenge our understanding. And yet, black holes are not merely destructive. They may play a central role in shaping galaxies. Observations show that most large galaxies harbour supermassive black holes at their centres, millions or even billions of times the mass of the Sun. These giants influence star formation through the energy they release, often in the form of powerful jets that stretch across thousands of light years. Paradoxically, by swallowing matter, they may help regulate the growth of galaxies, preventing them from forming stars too quickly. Once again, gravity proves itself as both a sculptor and a regulator of structure. Gravity also governs the largest scale of all, the evolution of the universe itself. In the early moments after the Big Bang, matter and radiation were nearly uniform, but tiny fluctuations in density grew under the influence of gravity. Over billions of years, these fluctuations became galaxies, clusters, and the cosmic web we see today. The balance between gravity and expansion has determined the history of the cosmos. At times, scientists debated whether gravity would one day halt expansion and cause a collapse. Today we know that dark energy is accelerating the expansion, but gravity still acts as the counterforce, pulling matter together into structures even as space itself stretches apart. It is fascinating to realize that gravity does more than shape space and time. It also shapes the flow of time itself. Because clocks run differently in different gravitational fields, time is not universal. A clock on the surface of the Earth runs more slowly than a clock in orbit. Astronauts on the International Space Station age very slightly faster than people on the ground. These effects are tiny in daily life, but essential for technology like GPS, which must correct for gravitational time differences to provide accurate positions. Gravity does not simply move matter, it defines the rhythm of existence. Another striking aspect of gravity is that we still do not fully understand it at the quantum level. The other forces of nature are described by quantum field theories, which explain interactions in terms of particles like photons or gluons. Gravity, however, resists easy quantization. The hypothetical particle that would mediate gravity, the graviton, has never been observed. Attempts to merge general relativity with quantum mechanics into a single theory of quantum gravity remain incomplete. String theory, loop quantum gravity, and other approaches seek to bridge the gap, but none are yet confirmed. This leaves gravity as both deeply familiar and profoundly mysterious. When you walk outside and see the moon in the sky, you're seeing gravity at work, holding it in orbit as it has for billions of years. When you look up at the Milky Way, stretching faintly across the night, you are seeing the result of gravity gathering stars into a spiral. When astronomers point their instruments at distant galaxies, they map the invisible scaffolding of gravity shaping the large-scale structure of the cosmos. Weak in the laboratory, overwhelming in the universe, gravity is the architect of structure, the quiet hand that builds order from chaos. The search for the most powerful thing in the universe cannot ignore this. Gravity may not release the most energy in a given second compared to a nuclear reaction or a burst of gamma rays, but it is the force that makes those events possible by gathering matter, compressing it, and setting the stage for fusion, collapse, and explosion. It is the context within which other powers act. Without it, the cosmos would be a thin haze of particles drifting apart, never forming stars, planets, or galaxies. When you look around your room right now, almost everything you see is shaped by one force. The light from a lamp or a screen, the structure of the objects around you, the colours of the walls or the fabric of the sheets, the sensation of your body resting where it touches the bed or the chair. All of these experiences are possible because of electromagnetism. It is the force that holds atoms together, the reason why matter has solidity, the explanation for why your eyes can see and your brain can process the world. If gravity sets the large-scale architecture of the universe, electromagnetism fills in the details, painting the surfaces, giving texture, and connecting the smallest scales to the most familiar parts of life. Electromagnetism is one of the four fundamental interactions of nature. Unlike gravity, which only attracts, electromagnetism has two charges, positive and negative. Like charges repel and opposite charges attract. These simple rules explain the structure of atoms. The positively charged protons in the nucleus attract the negatively charged electrons, holding them in orbit. At the same time, electrons repel each other, preventing them from collapsing into the nucleus. This balance creates stable atoms, and from atoms, molecules, and from molecules, everything around you. James Clerk Maxwell was the scientist who, in the 19th century, gave electromagnetism its most elegant description. His equations unified electricity and magnetism, showing that they are not separate phenomena but two aspects of the same force. Changing electric fields create magnetic fields, and changing magnetic fields create electric fields. Together, they form electromagnetic waves that travel through space at the speed of the light. Light itself is an electromagnetic wave, one small slice of a much broader spectrum that includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. The warmth you feel from the sun, the signal that carries your favourite song through the air, the colours you see every day, all of it is electromagnetic radiation. Electromagnetism is far stronger than gravity at the scale of atoms and molecules. If you touch a table, the reason your hand does not pass through it is not because the atoms are physically solid like tiny billiard balls. Instead, it is because the electromagnetic fields of the electrons in your hand repel the electromagnetic fields of the electrons in the table. What feels like solidity is actually electrical repulsion at a very small scale. Every time you stand, sit, pick something up, or place something down, you are interacting with electromagnetism. This force is also the foundation of chemistry. Chemical bonds between atoms arise from the sharing or transferring of electrons, governed entirely by electromagnetic interactions. The structure of DNA, the reactions that power your cells, the rusting of iron, the burning of wood, all of it is chemistry. And chemistry is nothing but electromagnetism at work between electrons and nuclei. Life itself depends on the way electromagnetism organizes matter into complex and flexible patterns. The range of electromagnetism is infinite like gravity, but because charges can cancel each other out, its influence beyond atoms is often hidden. A large object like a rock or a chair usually contains equal numbers of positive and negative charges, making it electrically neutral overall. That is why gravity dominates at large scales, even though electromagnetism is stronger. But when charges are separated, the effects become dramatic. A small build-up of static electricity can make your hair stand on end. A lightning bolt, which is just an enormous discharge of electrical energy between the sky and the ground, carries hundreds of millions of volts, heating the air hotter than the surface of the sun. The crack and flash you see during a storm is electromagnetism, releasing energy on a grand scale. Magnetism, too, is a direct consequence of this force. Moving charges create magnetic fields, and magnetic fields influence moving charges. That interplay explains why electric currents generate magnetism, why magnets can lift heavy pieces of metal, and why Earth itself acts like a giant magnet with poles. Without Earth's magnetic field generated by movements of molten iron in its core, the solar wind of charged particles from the sun would strip away the atmosphere, making life here impossible. The quiet shield that protects us every day is a gift of electromagnetism. If you look at the cosmos with radio telescopes, infrared detectors, or X-ray observatories, you're seeing different windows of the electromagnetic spectrum. Each reveals aspects of the universe invisible to the human eye. Radio waves map cold hydrogen clouds between stars. Infrared shows warm dust when new stars are forming. Ultraviolet highlights hot young stars. X-rays reveal violent environments around black holes and neutron stars. The electromagnetic force carries to us the story of the universe across billions of light years. Every photon that reaches your eyes or an instrument carries with it energy and information about where it came from. On Earth, humanity has learned to harness electromagnetism in profound ways. Generators spin coils of wire through magnetic fields to produce electricity. Motors use that electricity to produce motion. Circuits channel currents to perform calculations, sending signals that travel at nearly the speed of light. The entire modern world, from light bulbs to smartphones to MRI machines, is built on our understanding of this one force. Without electromagnetism, there would be no communication, no power grids, no medical imaging, no technology as we know it. The strength of electromagnetism compared to gravity becomes clear in even the simplest examples. A refrigerator magnet weighing a few grams can cling to a vertical door against the pull of the entire Earth. A small spark can leap across a gap, breaking down air molecules and producing light. At the atomic scale, the energy levels of electrons determine the colours of light absorbed and emitted, giving rise to the rainbow of chemical elements. At the cosmic scale, enormous magnetic fields thread through galaxies, guiding the motion of charged particles and shaping the structure of interstellar gas. From the smallest spark to the largest nebula, electromagnetism is everywhere. It is worth considering how deeply it influences not only the material world but our perception. Our eyes evolved to detect a narrow slice of the electromagnetic spectrum, the wavelengths of visible light. To us, that range defines what we call colour. But bees see into the ultraviolet. Snakes detect infrared. Radio telescopes reveal signals invisible to our senses. What we call reality is shaped by the sliver of electromagnetism we can directly perceive. The rest requires instruments to reveal, yet it is all the same underlying force. Electromagnetism also plays a role in the life of stars. Fusion reactions in stellar cores release charged particles and photons. The outer layers of stars are shaped by radiation pressure, a push exerted by light itself. When stars die, their remnants can produce some of the most powerful electromagnetic phenomena in the universe. Pulsars, which are rapidly rotating neutron stars with intense magnetic fields, sweep beams of electromagnetic radiation across space like cosmic lighthouses. Magnetars, a rare type of neutron star, have magnetic fields trillions of times stronger than Earth's. A single starquake on a magnetar can release as much electromagnetic energy as our sun emits in thousands of years. Even the vacuum of space reveals electromagnetic mysteries. Quantum electrodynamics, the theory describing how light and matter interact, shows that what appears to be empty space is full of virtual particles flickering in and out of existence. These interactions create subtle shifts in energy levels, measurable in experiments with astonishing precision. Electromagnetism is not only powerful, it is exquisitely accurate in its predictions. The agreement between theory and experiment in quantum electrodynamics is one of the most precise in all of science, sometimes to more than 10 decimal places. When we ask what is the most powerful thing in the universe, electromagnetism must always be in the conversation. It binds atoms, creates light, fuels chemistry, and shapes technology. It reveals the cosmos to us through radiation, while also protecting life on Earth with magnetic fields. Its strength is immense at small scales, overwhelming gravity in almost every local interaction. Its versatility makes it indispensable, for without it, the universe would be dark, structureless, and lifeless. And still, electromagnetism is only one piece of the story. Other forces are at work, hidden from daily experience but essential in ways that are no less profound. If you shrink your attention down from the world of atoms to what lies inside their nuclei, you enter a realm where forces behave in ways that are not part of everyday experience. At this scale, protons and neutrons sit together in the tiny core of the atom, packed so tightly that the distances between them are measured in trillionths of a meter. What makes this remarkable is that each proton carries a positive electric charge, according to the electromagnetic force like charges repel. By that reasoning, the protons inside a nucleus should fly apart immediately, driven away from each other by overwhelming repulsion, yet they stay bound together, forming stable nuclei that make up the matter of the universe. The reason they do not scatter is that another force, far stronger than electromagnetism, is at work. This is the strong nuclear force, the hidden titan of the subatomic world. The strong force operates only over extremely short ranges, but within that range, it dominates everything else. It is the strongest of the 4 known fundamental forces, about 100 times stronger than electromagnetism, and many orders of magnitude stronger than gravity. Its job is to hold protons and neutrons together inside atomic nuclei, providing the stability that allows matter to exist. Without it, no atoms heavier than hydrogen could survive. The universe would be a thin gas of isolated protons and electrons, unable to form the complexity we see around us. To understand how the strong force works, it helps to know what protons and neutrons themselves are made of. They are not indivisible particles. Each is composed of smaller constituents called quarks. A proton is built from 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. These quarks are bound together by the strong interaction, carried by particles called gluons. The name is apt, because gluons are the mediators of the force that glues quarks together. Unlike the photon of electromagnetism or the hypothetical graviton of gravity, gluons carry the very property they act upon. In electromagnetism, charges are positive and negative, and the photon itself is neutral. In the strong force, the equivalent property is called color charge, though it has nothing to do with visual colour. Gluons themselves carry colour, which means they can interact with each other as well as with quarks. This makes the mathematics of the strong force, known as quantum chromodynamics, complex and rich. It also makes the strong force unique in its behaviour. One striking aspect of the strong force is confinement. Quarks are never found alone. No matter how much energy you put into trying to separate them, the strong force grows stronger as they move apart. Imagine stretching a rubber band. The farther you pull, the greater the resistance. In the case of quarks, the energy put into separating them eventually creates new quark-antiquark pairs, rather than allowing a single quark to exist freely. This is why all observed particles are composites of quarks bound together, known as hadrons, with protons and neutrons being the most familiar examples. The strength of the strong force is also what powers stars. In stellar cores, nuclear fusion occurs when protons are pushed close enough together that the strong force can overcome their electromagnetic repulsion. At that moment, the strong force takes over, binding them into heavier nuclei and releasing vast amounts of energy. The light and heat we see from the Sun are ultimately products of the strong force acting inside atomic nuclei. Without this hidden titan, fusion would never ignite, and stars would never shine. The same principle explains the extraordinary energy of nuclear reactions on Earth. When nuclei split in fission or join in fusion, the rearrangement of protons and neutrons changes the balance of binding energy. A small difference in mass is converted into energy, according to Einstein's equation, E equals mc squared. The amounts may seem small at the scale of a single atom, but multiplied by the number of atoms in a kilogram of material, the energy release is immense. The destructive power of nuclear weapons and the potential of nuclear power plants both derive from the strong force and its binding energy. The hidden titan reveals itself in even more extreme events. In the death of massive stars, when gravity compresses matter to extraordinary densities, the strong force resists collapse. Neutrons, themselves bound by the strong interaction, are squeezed so tightly that they form neutron stars. These objects, only about 20 kilometers across but containing more mass than the Sun, are supported by the interplay of quantum mechanics and the strong force. Their existence is a testament to how powerful the strong interaction is when matter is compressed to unimaginable levels. If you go further into theory, the strong force also contributes to the stability of the vacuum itself. Quantum chromodynamics suggests that gluon fields permeate space, with virtual quark-antiquark pairs flickering in and out of existence. The energy of this quantum vacuum may influence the masses of particles, the behaviour of fields, and perhaps even the structure of the universe at large. The hidden titan is not only inside nuclei, it is woven into the very fabric of reality. Despite its strength, the strong force remains one of the most challenging to calculate precisely. Unlike electromagnetism, where equations can often be solved with high accuracy, the mathematics of quantum chromodynamics quickly becomes intractable. Physicists use powerful computers to simulate the interactions of quarks and gluons through methods known as lattice QCD. These simulations are among the most computationally demanding tasks in science, requiring supercomputers running for weeks or months. The reason is that the strong force does not diminish smoothly with distance, but grows stronger, creating a web of interactions that resist simple solutions. This difficulty highlights how much there is still to learn. While we can measure the outcomes of the strong force in experiments, like the behaviour of particles in accelerators, or the energy released in nuclear reactions, the deeper understanding of its full role in the cosmos is ongoing. It may be that hidden within the mathematics of the strong interaction are answers to questions about why matter has the structure it does, why the universe favours matter over antimatter, or why protons themselves are so stable, lasting billions of years without decay. It is worth reflecting on how something so central to existence can remain so hidden from daily life. You never feel the strong force directly. You cannot sense quarks or gluons with your hands or eyes, and yet everything solid, everything stable, everything enduring around you is made possible by it. Every nucleus in your body is a bundle of particles bound by this force. Every breath of oxygen, every sip of water, every movement of muscle depends on atoms that exist because the strong force holds them together. It is the quiet giant at the heart of matter, unseen but indispensable. When we compare the powers of the universe, the strong nuclear force deserves special attention. It is not visible like light, not far-reaching like gravity, not versatile like electromagnetism. But its strength is unmatched, and its consequences are profound. It ensures that matter exists in stable forms. It fuels the stars that give light and life. It shapes the most extreme objects, like neutron stars. And it challenges our theories with its complexity and depth. Among the four fundamental forces of nature, there is one that rarely gets much attention outside of physics circles. It is not as dramatic as gravity, which holds galaxies together, nor as visible as electromagnetism, which lights the sky with storms and stars. It does not display the raw strength of the strong nuclear force, which binds the very cores of atoms, and yet without it, stars could not shine, elements could not form, and life itself would never have come to be. This quiet but indispensable actor is the weak nuclear force, sometimes simply called the weak interaction. Its name makes it sound minor, but its role is essential. The weak force governs processes of change within particles. While the strong force holds protons and neutrons together, the weak force allows them to transform into one another. A neutron can decay into a proton, releasing an electron and a particle called an antineutrino. This process, known as beta decay, is one of the most important mechanisms in nuclear physics. It is the weak force that makes this possible, turning one type of particle into another and releasing energy in the process. Think about what this means for the universe. In the heart of stars, fusion reactions depend not only on the strong force, which binds nuclei once they are close enough, but also on the weak force, which allows the reactions to proceed in the first place. In our Sun, for example, the chain of reactions that fuses hydrogen into helium begins with two protons colliding. Normally, because they're both positively charged, they repel each other, but occasionally, through quantum tunneling and under the immense pressures of the solar core, they come close enough for one to transform. One of the protons becomes a neutron, thanks to the weak force, producing a deuterium nucleus, a positron, and a neutrino. Without this step, fusion would never start and the Sun would be dark. The weak interaction is also the reason neutrinos exist in such abundance. Neutrinos are incredibly light, neutral particles that rarely interact with matter. Trillions of them pass through your body every second without leaving a trace. They are produced in vast numbers in stars and supernovae through weak interactions. Despite their elusive nature, they carry away a significant fraction of the energy from these processes, acting as silent messengers of nuclear change. Detecting neutrinos on Earth requires enormous underground detectors filled with water or special materials shielded from other particles, waiting for the rare moment when a neutrino collides with an atom. These faint signals tell us about what is happening in the distant universe, carried by particles that almost never interact. The weak force is short-ranged, even more so than the strong force. Its influence extends only across distances much smaller than the size of an atom. This is because it is mediated by massive particles, the W and Z bosons. Unlike the photon of electromagnetism or the gluons of the strong force, which are massless, these bosons are heavy, with masses about 90 times that of a proton. Their heaviness limits the reach of the weak interaction, confining it to the tiniest scales. But within that small range, the weak force plays a role that nothing else can. It violates certain symmetries that other forces respect. For instance, it is not symmetrical with respect to mirror reflection. Imagine looking at a process in a mirror. Most forces behave the same whether you view them directly or in reflection. The weak force does not. It distinguishes left from right, a property known as parity violation. This strange behaviour was first discovered in the 1950s and shocked physicists at the time. It suggested that the universe itself has a built-in handedness, a subtle asymmetry woven into its fabric. The weak interaction may also be connected to one of the deepest mysteries in cosmology: why the universe is made of matter rather than antimatter. In theory, the Big Bang should have produced equal amounts of both. When matter and antimatter meet, they annihilate into energy. If the amounts had been exactly balanced, they would have cancelled out completely, leaving nothing but radiation. Yet here we are, in a universe filled with matter. Something tipped the balance. Some processes in the weak interaction violate the symmetry between matter and antimatter, a phenomenon called CP violation. While the amount observed so far is not enough to fully explain the imbalance, it is a clue that the weak force may have played a role in creating a universe that contains stars, planets, and people. In everyday life, the weak force is at work quietly. Radioactive decay, which occurs naturally in many elements, is driven by weak interactions. The glow of uranium, the ticking of Geiger counters, the decay heat that continues in nuclear reactors even after shutdown, all are products of the weak force. Medical imaging techniques like PET scans also rely on it, detecting the positrons emitted when certain isotopes undergo beta decay. Even though you cannot feel the weak interaction directly, its fingerprints are present in medicine, geology, and technology. To appreciate its significance, consider again the life cycles of stars. When massive stars run out of fuel, their cores collapse under gravity. In these extreme conditions, the weak force governs the transformations of particles, turning protons into neutrons and filling the collapsing core with neutrinos. These neutrinos escape in enormous numbers, carrying away energy and triggering the explosion we see as a supernova. Without the weak interaction, supernova could not release their energy so dramatically. Heavy elements, forged in those explosions, would not be scattered into space. Planets like Earth, and the life that depends on carbon, oxygen, and iron, would never have formed. The weak force's name makes it sound unimpressive, but it is not about strength in the usual sense. It is about transformation. It is the force of change, turning particles into other particles, enabling processes that would otherwise be impossible. It is less about holding things together, like gravity or the strong force, and more about allowing them to evolve. In this way, it is small but essential, a quiet engine of cosmic progress. What makes the weak interaction even more remarkable is how well it fits into the larger framework of physics. In the 20th century, physicists discovered that the weak force and electromagnetism are actually two aspects of a single unified interaction called the electroweak force. At high energies, such as those present shortly after the Big Bang or in particle accelerators today, the distinction between the weak and electromagnetic forces disappears. They merge into one. This unification was a triumph of modern physics, confirmed by experiments at particle colliders that observed the W and Z bosons directly. It suggests that at even higher energies, perhaps the strong force and gravity might also join in a grander unification. The weak force also plays a role in shaping the age of the universe. The half-lives of radioactive elements determined by weak interactions provide clocks that let scientists date rocks, fossils, and even the Earth itself. By studying the ratios of isotopes in meteorites, geologists and astrophysicists can trace the history of the solar system. By analysing the decay of uranium to lead, they estimate the Earth's age at about 4.5 billion years. These clocks tick not with gears or electronics, but with the quiet transformations of the weak force unfolding over eons. Think again about the scale of influence here. Gravity controls the motion of galaxies. The strong force binds the cores of atoms. Electromagnetism fills our world with light, chemistry, and technology. The weak force, invisible and elusive, determines how stars burn, how elements form, how supernovae explode, how isotopes decay. how matter itself may have triumphed over antimatter, it is not measured in the same terms of sheer strength, but in terms of necessity. Without it, the cosmic story would stop before it even began. And so, as we look at what might be the most powerful thing in the universe, we must keep in mind that power is not always obvious. Sometimes it is quiet, hidden, and essential, enabling everything else. The weak nuclear force is one of those hidden enablers. Light is so ordinary in daily life that it can be easy to forget how extraordinary it really is. You flip a switch, and a bulb fills the room with brightness. The sun rises, and the world changes from shadow to clarity. A candle burns, and its small flame can make an entire space feel alive. Yet light is not only a convenience, not only a comfort. In physics, it is one of the most fundamental ways that energy moves. Light is energy on the move, carried across space as electromagnetic radiation, travelling at the fastest speed the universe allows. From the perspective of physics, light is a stream of photons, particles without mass that carry energy and momentum. These photons travel at about 300,000 kilometers per second, crossing the distance from the Sun to Earth in just over 8 minutes. That speed is not simply fast, it is a cosmic limit. Nothing with mass can move faster. Information, signals, energy, everything that moves from place to place must obey the same constraint. In this sense, light defines the maximum pace of causality in the universe. When James Clerk Maxwell wrote down his equations in the 19th century, he showed that electric and magnetic fields could combine to form waves that propagate through space. The speed of those waves matched the measured speed of light. This was the revelation. Light itself is an electromagnetic wave. From that realization came the understanding that radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays are all the same phenomenon, differing only in wavelength and frequency. The visible spectrum is just a sliver, a narrow window to which our eyes evolved to be sensitive, but the electromagnetic spectrum extends far beyond what we can see. What makes light remarkable is that it carries energy and information without needing any medium. Sound requires air, water, or another substance to move through, but light travels through the vacuum of space. A photon leaving a star in a distant galaxy can journey for billions of years, never stopping, never slowing, until it reaches a telescope or the surface of a planet. The uninterrupted travel makes light the messenger of the cosmos. Nearly everything we know about the universe beyond Earth comes from light. Telescopes capture it, spectrometers analyze it, detectors measure its polarization, and through those observations we infer the temperatures, motions, and compositions of objects unimaginably far away. Light is not only a wave, quantum mechanics revealed that it is also a particle, exhibiting behavior that cannot be explained by classical waves alone. In the famous double-slit experiment, individual photons produce interference patterns over time, behaving as if each photon is both a particle and a wave simultaneously. This duality is one of the central mysteries of quantum physics, and it is not unique to light. Electrons, atoms, and other particles also display wave-particle duality. But with light, the effect is especially striking, because photons are so fundamental to our experience and to our measurements of reality. The energy of a photon depends on its frequency. Low-frequency photons like radio waves carry very little energy. High-frequency photons like gamma rays carry enormous energy, capable of altering nuclei and triggering reactions. This wide range makes the electromagnetic spectrum not just a curiosity, but a toolbox for science. Astronomers use radio waves to study cold hydrogen gas, infrared to observe warm dust clouds, visible light to map stars, ultraviolet to trace hot young stars, X-rays to see the environments of black holes, and gamma rays to investigate the most violent explosions in the universe. Each band of light tells a different part of the cosmic story. Here on Earth, life itself is tied to light. Photosynthesis captures energy from sunlight, storing it in chemical bonds that feed ecosystems. Human vision depends on photons striking cells in the retina, triggering signals to the brain. Circadian rhythms, the daily cycles of wake and sleep, are regulated by the rising and setting of light. Our entire sense of time and rhythm is connected to the movement of light across the sky. Even our technologies, from fiber optic cables transmitting data as pulses of light to lasers used in medicine and manufacturing, rely on the controllable movement of photons. Light is also a source of pressure. It might not seem intuitive, but photons, though massless, carry momentum. When they strike a surface, they exert a tiny push. On Earth, that push is too small to notice in daily life, but in space, with no air resistance and vast expanses of time, light pressure can move objects. Spacecraft with large reflective sails, called solar sails, can be propelled across the solar system by the steady stream of photons from the Sun. Comet tails bend away from the Sun, in part because of light pressure, with photons nudging dust and gas outward. The idea that light is not only illumination but also a source of mechanical force shows just how versatile this phenomenon is. When physicists study the early universe, they see that light was central even there. In the first few 100,000 years after the Big Bang, the universe was hot and dense, filled with a plasma of particles and radiation. Photons scattered constantly off charged particles, unable to travel freely. As the universe expanded and cooled, atoms formed, and photons could finally move unhindered. Those photons are still travelling today, stretched into microwaves by the expansion of space, forming what we call the cosmic microwave background. This faint glow, detected in every direction, is a snapshot of the universe when it was only 380,000 years old. It is one of the most important pieces of evidence for cosmology, a message carried by light across nearly 14 billion years. The interaction of light with matter is also the basis of quantum electrodynamics, one of the most precise and successful theories in physics. This framework describes how photons interact with charged particles, predicting outcomes that experiments have confirmed to astonishing precision. The agreement between theory and experiment is sometimes as close as 1 part in 10 billion. That level of accuracy demonstrates not only the reliability of light as a concept in physics, but also its central role in the laws that govern reality. Light also defines the boundaries of possibility in physics. Because nothing can travel faster than light in a vacuum, it sets the cosmic speed limit. This means that information, signals, and causality itself cannot exceed that pace. When you look at a star, you are seeing it not as it is now, but as it was when its light began its journey. A star 100 light-years away is seen as it was a century ago. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. Light is not just a messenger, it is a time machine of sorts, showing us the past. Every night skies a mosaic of history, with each point of a light representing a different age of the universe. What makes light especially intriguing in the context of power is the sheer energy it can transport. The sun releases 3.8 times 10 to the power of 26 watts, and most of that energy leaves as light and radiation. When a supernova explodes, the burst of photons can briefly outshine an entire galaxy. When matter falls into a black hole, the process of heating and accelerating it before crossing the event horizon produces jets of light across the spectrum, some of the brightest events known. Gamma-ray bursts, which may result from collapsing massive stars or merging neutron stars, release more electromagnetic energy in a few seconds than the sun will emit in its 10 billion year lifetime. These are moments when light is not gentle illumination but a torrent of energy sweeping across space, and yet despite its power, light also has a fragility to it. Photons can be absorbed, scattered, or redshifted. Their energy can be stretched thin by the expansion of the universe. They can be delayed by interactions with matter along their journey. This dual nature, immense in energy yet delicate in travel, adds to the fascination of light as energy in motion. In comparing the powers of the universe, light is both an answer and a pathway to answers. It is what allows us to know anything beyond our immediate surroundings. Without it, the cosmos would be invisible, unknowable, silent. But through it, we see stars being born, galaxies colliding, and the glow of the earliest times. Light is not only energy on the move, it is knowledge on the move. When you look into the night sky, every point of light you see, apart from the planets and the occasional reflected glimmer from a satellite, is a star. From Earth, they appear as tiny specks, fragile dots scattered across darkness. But in reality, they are vast engines, incomparably larger than our world, burning with processes that transform the simplest element, hydrogen, into heavier elements and light. Stars are engines of fusion, and through them, the universe takes raw material and turns it into energy and complexity. The story of a star begins in a cloud of gas and dust. These clouds drift through galaxies, sometimes spanning hundreds of light years, cold and dark in most places. But within them, small regions can grow dense, pulled together by gravity. As the material collapses, it heats up, the pressure rising in the centre. Eventually, if the mass is sufficient, the temperature climbs high enough that hydrogen nuclei begin to fuse. At that moment, a star is born. Fusion is not easy. Hydrogen nuclei, which are protons, repel each other strongly because of their positive electric charges. To bring them close enough for the strong nuclear force to take over and bind them requires immense pressure and temperature. In the core of the Sun, conditions reach about 15 million degrees Celsius. At that temperature, protons move fast enough that occasionally, through quantum tunneling, they can slip close enough to one another for the strong force to act. When they do, they fuse, producing helium and releasing energy. This process converts mass into energy. Following Einstein's equation, E equals mc squared. The difference in mass between the starting particles and the final products becomes energy in the form of photons and neutrinos. In the Sun, this happens about 600 million times per second, with enormous amounts of hydrogen converted into helium. The energy release travels outward through layers of plasma, bouncing from particle to particle, slowly making its way to the surface. The photons that finally escape have often spent tens of thousands of years inside the Sun, scattering countless times before reaching open space. From there, they travel across the vacuum of space to Earth, arriving as sunlight, the energy that drives our climate, our ecosystems, and our lives. Fusion is the defining feature of stars. It is what makes them shine steadily for billions of years. Different stars follow different fusion pathways depending on their mass and temperature. In stars like the Sun, the dominant process is the proton-proton chain, where protons fuse step by step into helium. In more massive stars, another process called the CNO cycle becomes dominant, using carbon, nitrogen and oxygen as catalysts to speed fusion. Both processes achieve the same outcome, turning hydrogen to helium and releasing vast amounts of energy. The balance inside a star is delicate. Gravity pulls inward, trying to collapse the star. Fusion pushes outward, producing pressure through the release of energy. For most of a star's life, these two forces remain in equilibrium, creating stability. The star neither collapses nor explodes but shines steadily. The larger the star, the faster it burns its fuel. Small stars, called red dwarfs, burn slowly and can last for trillions of years. Massive stars, tens of times the mass of the Sun, burn furiously, consuming their hydrogen in only a few million years before ending their lives dramatically. Stars are not only engines of energy but also forgers of elements. As hydrogen is consumed, helium builds up in the core. When hydrogen runs low, the core contracts, heating up further until helium fusion becomes possible. Helium fuses into carbon and oxygen. In the most massive stars, the process continues, building heavier and heavier elements from neon to magnesium, silicon, and eventually iron. Fusion of elements lighter than iron releases energy, but iron is different. Fusing iron does not release energy, it consumes it. When a star builds up an iron core, it has reached the end of the road for fusion. At that point, gravity wins, the core collapses, and the star's life enters a new phase, often ending in a supernova. But long before that violent finale, stars have already changed the universe profoundly. The first stars that formed after the Big Bang contained only hydrogen and helium. Through their lifetimes and deaths, they created heavier elements and spread them into space. Later generations of stars incorporated those elements, leading to planets, chemistry, and eventually life. The oxygen you breathe, the carbon in your body, the calcium in your bones, the iron in your blood. All were forged in the cores of stars and released into space by stellar winds or explosions. Stars are not just engines of fusion, they're cosmic alchemists, transforming simplicity into diversity. The power of fusion in stars is almost beyond comprehension. The Sun releases about 3.8 times 10 to the 26 watts of energy continuously. To put that in perspective, humanity's total energy consumption is about 10 to the power of 13 watts, a fraction so small that it hardly registers next to the Sun's output. And yet the Sun is an ordinary star, neither especially large nor especially bright. Other stars are far more extreme. A blue giant may radiate thousands of times more energy than the Sun. Supernovae release in a few seconds as much energy as the Sun will release in its entire 10 billion year lifetime. Fusion is not only central to stars but also to our own technological dreams. On Earth, scientists strive to replicate stellar fusion in reactors, confining hot plasma with magnetic fields or lasers, hoping to achieve a controlled reaction that produces more energy than it consumes. If successful, fusion could provide nearly limitless clean energy, using hydrogen from water as fuel and producing helium as a byproduct. The challenge is immense, because sustaining the conditions of millions of degrees without losing energy to the environment is no small task. But the fact that stars do this naturally, maintaining fusion for billions of years, is both an inspiration and a reminder of how finely tuned the processes of nature can be. Fusion also illustrates the interplay of forces. Gravity compresses matter until fusion ignites. The strong nuclear force binds protons and neutrons once they are close enough. The weak force enables certain transformations that make the reactions possible. Electromagnetism carries away the energy as photons that eventually leave the star. All four fundamental interactions are involved in the life of a star, working together in a delicate balance. Stars are the laboratories where these forces converge and reveal their collective power. As you imagine the night sky, filled with countless points of light, remember that each one is a self-sustaining engine, fusing hydrogen into helium, radiating energy across space, and slowly transforming the universe. Some burn quietly for billions of years, others live fast and die young in brilliant explosions, but all of them are part of a cosmic cycle, engines that keep the universe active, illuminated, and evolving. The quiet glow of a star can last for billions of years, a steady balance between the inward pull of gravity and the outward pressure of fusion. But even stars cannot last forever. When the fuel in their cores begins to run out, when fusion can no longer provide enough outward push to hold gravity at bay, some stars meet an end that is anything but quiet. These endings are violent, luminous, and spectacular, releasing more energy in a brief moment than the Sun will emit in its entire lifetime. They're called supernovae, and they are among the most powerful events the universe produces. The path to a supernova depends on the mass of the star. In smaller stars like our Sun, the end comes more gently. The outer layers drift away, forming glowing shells called planetary nebulae, while the core cools into a white dwarf. But in stars much more massive than the Sun, gravity eventually overwhelms every resistance. When such a star exhausts its fuel, its core collapses, and the result is an explosion of almost unimaginable intensity. In a massive star, fusion progresses through stages. First hydrogen fuses into helium, then helium into carbon and oxygen, and in the larger stars fusion continues into heavier elements like silicon and sulfur. Each step requires higher temperatures and pressures, and each step releases energy that helps to balance gravity. But the process cannot go on forever. Once iron builds up in the core, fusion can no longer provide energy, because fusing iron consumes energy instead of releasing it. The star has reached a dead end. Gravity, relentless and unopposed, forces the core inward. The collapse happens in less than a second. The core, with more mass than the Sun, shrinks to the size of a city. In that instant, protons and electrons are squeezed together into neutrons, releasing a flood of neutrinos. The outer layers of the star, unable to keep falling inward, rebound against the dense neutron-rich core. The shock wave blasts outward, tearing the star apart in an explosion that can be brighter than an entire galaxy. For days or weeks, the supernova shines so intensely that it can be seen across millions of light years. Then gradually it fades, leaving behind a neutron star or, if the mass is great enough, a black hole. The energy released in a core collapse supernova is staggering. In just a few seconds, about 10 to the power of 44 joules of energy are emitted. Most of this leaves as neutrinos, particles that stream through matter almost without interaction. A smaller fraction is converted into light, but even that smaller fraction is enough to outshine billions of stars for a brief time. To put it into perspective, the light from a single supernova can equal the combined output of every star in a galaxy. It is no wonder that these explosions have been noticed and recorded by people throughout history. Supernovae are not only spectacular, they are essential for the universe's story. The heavy elements forged in the cores of stars cannot remain locked away. They must be scattered into space, mixed into clouds of gas, and recycled into new generations of stars and planets. The carbon in your cells, the oxygen in your lungs, the iron in your blood, the gold in your jewellery. All of it was made in stars and dispersed by supernovae. Without these explosions, the universe would contain only hydrogen and helium, with none of the diversity required for planets or life. Supernovae are both endings and beginnings, destroying stars while seeding the raw materials for new ones. There is another type of supernova that follows a different path but ends with equal brilliance. White dwarfs, the remnants of smaller stars, can sometimes find themselves in binary systems with a companion. If the white dwarf pulls in matter from its partner, it can grow until it reaches a critical mass known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. At that point, it can no longer support itself. The sudden ignition of runaway fusion rips the star apart in a thermonuclear explosion. These events, known as Type 1 supernovae, are important in another way. Because they always occur at roughly the same mass and therefore the same brightness, they serve as standard candles in astronomy. By comparing their known luminosity to their observed brightness, astronomers can measure cosmic distances with remarkable accuracy. It was through the study of Type I supernovae in the late 20th century that scientists discovered something astonishing. The expansion of the universe is accelerating. The light from distant supernovae appeared dimmer than expected, suggesting they were farther away than predicted. The only explanation was that the expansion of space had sped up, driven by a mysterious component we now call dark energy. In this way, supernovae not only tell the story of stars but also reveal the fate of the cosmos. Supernovae also produce some of the most exotic remnants in existence. If the collapsed core is less than about 3 times the mass of the Sun, it stabilizes as a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. Neutron stars can rotate rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. Some develop magnetic fields trillions of times stronger than Earth's, becoming magneteers that unleash bursts of energy capable of disrupting instruments across vast distances. If the core is more massive still, gravity wins entirely and a black hole forms. These remnants, products of supernovae, are themselves among the most powerful and mysterious objects in the universe. The violence of a supernova may seem almost chaotic, but it follows clear rules of physics. Gravity, nuclear forces, and particle interactions all play their roles. The collapse releases energy in the form of neutrinos. The shockwave propagates outward, energized by those same neutrinos. Fusion briefly reignites in the outer layers, producing elements heavier than iron, including gold and uranium. The star tears itself apart, enriching the cosmos. It is destruction and creation woven together in one event. For astronomers, supernovae are not only fascinating phenomena, but also essential tools. By observing their light curves, the way their brightness changes over time, scientists classify them, understand their mechanics, and measure cosmic distances. By analysing their spectra, they learn which elements were produced. By detecting the neutrinos and gravitational waves they emit, physicists probe the fundamental forces of nature under conditions impossible to replicate on Earth. Every supernova is a laboratory, an opportunity to test theories at the limits of energy and density. Even in human history, supernovae have left their marks. In the year 1054, observers in China recorded the sudden appearance of a new star in the sky, bright enough to be seen in daylight for weeks. That event was the supernova that created the Crab Nebula, which we now observe with telescopes as a glowing cloud of gas expanding from the explosion center. Similar records exist from other cultures, showing that humanity has always noticed these cosmic outbursts, even before their true nature was understood. To those who witnessed them, they must have seemed like miracles or omens, sudden lights appearing in the heavens without warning. Today we know they are stars dying, but the sense of awe remains. The power of a supernova cannot be overstated. In the moments of explosion, the output dwarfs anything else we can observe directly. And yet, supernovae are not rare in the universe. In a galaxy like the Milky Way, they occur roughly once every century. Across the hundreds of billions of galaxies we can see, they are happening somewhere almost constantly. The cosmos is alive with explosions, each one a step in the endless cycle of star birth, life, and death. What makes them especially significant in our exploration of power is that they represent a turning point. Stars spend billions of years steadily burning hydrogen. Then, in a flash of collapse and explosion, they release energy at a rate that redefines scale. They illustrate how the balance of forces, gravity, nuclear fusion, electromagnetism, can suddenly shift, unleashing stored potential in a final act of brilliance. They are a reminder that the universe is not static, that even seemingly eternal stars can end in fire and light. There are places in the universe where gravity has gone so far beyond what we experience on Earth that ordinary intuition can no longer guide us. These are regions where matter has been compressed so much that nothing can resist its pull, not even light. Once something crosses the threshold into this realm, there is no return. These objects are black holes, and they are among the most powerful phenomena in existence, born from collapse, shaped by the very fabric of space-time, and surrounded by mysteries that still challenge physics. The idea of a black hole begins with gravity taken to its ultimate extreme. Imagine compressing the Earth down into the size of a marble. Its gravity would become so intense that even photons, which normally travel freely through the vacuum of space, could not escape. This boundary, the point of no return, is called the event horizon. Anything that crosses it is lost to the outside universe, carried inward toward a central region called the singularity, where density becomes infinite and the known laws of physics cease to apply. Black holes are not simply dense objects. They are regions of space-time where geometry itself is curved so steeply that escape is impossible. The most common way black holes form is from the deaths of massive stars. When such a star exhausts its fuel, the outward pressure from fusion ceases. Gravity takes over, collapsing the core. If the remaining mass is above a certain threshold, even neutron degeneracy pressure, the resistance of neutrons packed together, cannot halt the collapse. The core shrinks past all limits, and a black hole is born. Its mass is concentrated within the event horizon, its presence detectable only through its influence on the surrounding environment. Black holes reveal themselves in several ways. One is through their gravitational pull on nearby stars. Astronomers can observe stars orbiting around invisible centers, their motions betraying the presence of massive unseen companions. Another is through the radiation emitted as matter falls toward the event horizon. Gas spirals in, forming an accretion disk. As it accelerates and heats, it emits light, often in the X-ray range. These emissions allow us to detect black holes across the cosmos, even though the holes themselves emit no light. In some cases, black holes produce jets, streams of particles moving at nearly the speed of a light, launched outward from the regions near the event horizon. These jets can stretch for thousands or even millions of light years, visible across vast cosmic distances. The exact mechanism behind jet formation is still studied, but it involves magnetic fields and the immense energies of rotating black holes and their accretion disks. These jets demonstrate the paradoxical nature of black holes. Objects defined by their ability to swallow everything can also be the sources of some of the brightest and most powerful phenomena in the universe. Black holes also come in different sizes. Stellar mass black holes formed from collapsing stars range from a few to perhaps a few dozen times the mass of the Sun. At the other extreme are supermassive black holes, millions to billions of times the Sun's mass, found at the centers of galaxies. The black hole at the heart of our Milky Way, called Sagittarius, a star, has a mass of about 4 million suns. Even more massive examples exist in other galaxies. The largest known may exceed tens of billions of solar masses, anchoring entire clusters of galaxies. How these giants form is still debated, but they are central to galactic evolution. Their gravity shapes the motions of stars, and their activity influences star formation across whole galaxies. In between the stellar and supermassive categories, there may exist intermediate mass black holes, though they are harder to confirm. These would bridge the gap, showing how black holes grow from smaller seeds into cosmic behemoths. Evidence is accumulating from observations of star clusters and gravitational wave detections, suggesting that such middleweights do exist, adding another layer to the black hole population. Perhaps the most striking way black holes demonstrate their power is through gravitational waves. When two black holes spiral into each other and merge, they send ripples through space-time itself. These waves were predicted by Einstein's general relativity and first detected in 2015 by the LIGO Observatory. The signal came from two black holes colliding over 1 billion light-years away, releasing energy in the form of gravitational waves equivalent to several solar masses converted directly to pure radiation. For a fraction of a second, that merger emitted more power than all the stars in the observable universe combined. Events like this remind us that black holes are not just theoretical curiosities, but engines of cosmic-scale energy. The physics near a black hole is full of strange consequences. Time, for example, does not flow the same way near an event horizon as it does far away. For a distant observer, a clock falling toward the horizon seems to slow down, ticking more and more slowly as it approaches the edge, never quite crossing it. For the falling clock itself, time feels normal, but it passes into the black hole in finite moments. This difference, called gravitational time dilation, is a consequence of space-time curvature and shows how deeply black holes challenge our understanding of reality. Another feature is the possibility of Hawking radiation, a quantum mechanical process proposed by Stephen Hawking in the 1970s. According to this theory, black holes are not entirely black. Quantum fluctuations at the event horizon allow pairs of particles to form, with one escaping and the other falling in. The result is a slow emission of radiation, causing the black hole to lose mass over incredibly long timescales. For stellar or supermassive black holes, the effect is negligible compared to other processes, but for tiny black holes, it could be significant. If true, this process means that black holes are not eternal. They will eventually evaporate. Despite decades of research, black holes still raise unresolved questions. What exactly happens at the singularity, the central point of infinite density? Is it truly infinite, or does a theory of quantum gravity smooth it out? What happens to information that falls into a black hole? Quantum mechanics insist that information cannot be destroyed, but general relativity suggests that it disappears beyond the event horizon. This tension is called the information paradox, and it remains one of the deepest puzzles in physics. Solving it may require a new understanding that unifies relativity and quantum mechanics. Black holes also expand our imagination about what is possible. Could they be gateways to other universes, as some speculative ideas suggest? Could their event horizons hide structures we do not yet understand? Most of these ideas remain in the realm of theory and speculation, but they show how black holes push the boundaries of both observation and thought. They are natural laboratories where gravity reaches its ultimate expression, where space and time themselves are bent into unfamiliar shapes. For all their strangeness, black holes are part of the ordinary life cycle of matter. They form from stars, they shape galaxies, they collide and merge, and they may even influence the expansion of the universe. They are woven into the cosmos not as exotic exceptions, but as common players, with millions of them likely scattered throughout the Milky Way alone. The fact that something so extreme can be so widespread is a measure of just how powerful gravity is when taken to its limit. As we follow this exploration of power, black holes represent one of the most compelling stops. They embody gravity unleashed, stripped of moderation, concentrated to the point where escape is impossible. They produce events of extraordinary energy, from accretion disks blazing with X-rays to mergers shaking space-time. They challenge our theories and force us to ask questions about the nature of reality itself. When a massive star reaches the end of its life and collapses, not every remnant becomes a black hole. In many cases, the collapse stops just short of that final step, leaving behind an object that is no less extraordinary. These remnants are neutron stars, some of the strangest and most extreme pieces of matter in the universe. They are so dense that they compress the mass of the Sun into a sphere only about 20 kilometers across. They sit at the edge of what matter can become before gravity overwhelms everything, and in their properties we find some of the most remarkable demonstrations of physics. A neutron star forms during a core collapse supernova. As the star's core runs out of fuel and gravity takes over, protons and electrons are forced together into neutrons. Neutrinos escape in enormous numbers, carrying away energy. What remains is a ball of neutrons packed so tightly that the structure is supported not by ordinary pressure, but by neutron degeneracy pressure, a quantum mechanical effect that resists further collapse. The balance holds, creating a stable object that is no longer a star in the usual sense, but not yet a black hole. To imagine the density of such an object, consider a teaspoon of neutron star material. That tiny amount would weigh billions of tons, more than a mountain on Earth. The surface gravity is so strong that if you stood on it, which is impossible in practice, you would be crushed instantly by a pull billions of times stronger than Earth's. Escape velocity from the surface is about half the speed of light. Space itself curves sharply around such an object, bending light and time in ways that defy normal intuition. Neutron stars are not uniform. Their interiors are layered, with a crust of atomic nuclei and electrons on the outside, and deeper layers where neutrons dominate. Some theories suggest that at even greater depths, exotic forms of matter might exist, such as hyperons, particles containing strange quarks, or even quark matter itself, where neutrons dissolve into a soup of quarks. These possibilities are difficult to test directly, but they make neutron stars important laboratories for physics at densities far beyond anything achievable on Earth. Many neutron stars reveal themselves through their rotation. When a neutron star is born, it can spin incredibly rapidly because the collapse of the star conserves angular momentum. A star that once rotated once every few days can shrink down and rotate dozens or hundreds of times per second. These rapidly spinning neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star spins, the beams sweep across space like lighthouse beams. If Earth lies in the path of the beam, we observe regular pulses of radio waves, X-rays, or even gamma rays. Some pulsars are so precise that they're timing rivals atomic clocks, making them useful tools for studying the universe. The magnetic fields of neutron stars are another extraordinary feature. Because the star's collapse concentrates its magnetic field along with its mass, neutron stars can have magnetic fields trillions of times stronger than Earth's. In some cases, these become magnetars, neutron stars with magnetic fields so intense that they can twist their crusts and release bursts of radiation powerful enough to affect instruments across light years of distance. A single flare from a magnetar can release more energy in a fraction of a second than the sun emits in 100,000 years. These are some of the most energetic events we can detect in the cosmos, produced by objects only a few kilometers wide. Neutron stars also provide crucial insights through collisions. When two neutron stars spiral together and merge, the event releases gravitational waves, ripples in space-time that we can detect with instruments like LIGO and Virgo. The first detection of such a merger in 2017 provided not only gravitational wave data, but also light across the spectrum, from gamma rays to radio waves. This was a breakthrough in astronomy, allowing scientists to study the same event through multiple messengers. The merger also produced heavy elements, such as gold and platinum, forged in the extreme conditions of colliding neutron stars. In that moment, we saw that some of the most precious materials on Earth were born in cosmic cataclysms far away. For astrophysicists, neutron stars are natural laboratories for physics that cannot be recreated elsewhere. The densities inside them test the limits of nuclear physics, quantum mechanics, and relativity. Observations of their sizes, masses, and behaviors help constrain theories of matter under extreme conditions. Even questions like the maximum possible mass of a neutron star remain open. If a neutron star becomes too massive, it will collapse into a black hole. Pinpointing that threshold helps scientists understand the equations of state for nuclear matter, the relationships between pressure, density, and temperature at scales beyond any laboratory. Neutron stars also play roles in the dynamics of galaxies. Their strong magnetic fields and radiation affect surrounding gas. Their mergers contribute to the enrichment of the interstellar medium. Their high velocities, sometimes reaching hundreds of kilometers per second after the supernova that created them, send them racing across galaxies like cosmic cannonballs. Though tiny compared to stars, they have an influence far beyond their size, shaping their environments and contributing to the broader cycles of matter. The existence of neutron stars also connects to questions about the ultimate fate of matter. If you compress neutrons further, do they remain neutrons, or do they dissolve into quarks and gluons, creating a quark star or even stranger forms of matter? The answers lie beyond current observations, but they hint that neutron stars may not be the final step before black holes. Instead, they may be transitional states, windows into new physics that could explain not only the behavior of dense matter, but also the history of the universe itself. The study of neutron stars continues to expand with new instruments. X-ray observatories, radio telescopes, and gravitational wave detectors all provide different views of these objects. By combining data, scientists refine their understanding of neutron star structure and behavior. Each discovery adds detail to the picture: how fast they spin, how strong their magnetic fields are, how they cool over time, and how they interact with their surroundings. Every pulse, flare, and merger is a clue to the physics of matter under conditions that stretch our theories. It is remarkable to think that objects only a few kilometers wide can rival entire galaxies in the energies they release during certain events. Neutron stars show that power in the universe does not always come from size alone. Sometimes it comes from density, from the concentration of matter into forms that push the boundaries of physical law. They are proof that nature finds ways to compress, concentrate, and release energy in ways far beyond our everyday experience. When astronomers look at the universe and try to measure how much matter it contains, the numbers do not add up. The stars, planets, gas, and dust that we can see account for only a fraction of what must be there. Galaxies spin too quickly for their visible matter to hold them together. Clusters of galaxies bend light more strongly than their observed mass can explain. Across scales both large and small, something invisible is exerting gravity, outweighing all the luminous matter combined. This hidden substance is what scientists call dark matter, and it is one of the most silent yet influential components of the cosmos. The name can be misleading. Dark matter is not simply matter that is dim or hidden behind dust. It is not ordinary matter at all, at least not in the forms we know: atoms, protons, neutrons, and electrons. Instead, it is thought to be made of entirely different particles, ones that do not interact with light. They do not emit, absorb, or scatter electromagnetic radiation. That is why we cannot see them with telescopes. Their presence is inferred only through gravity. The story of dark matter begins with the motions of galaxies. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a collection of galaxies bound together by gravity. He found that the galaxies were moving so fast that the visible matter was not enough to hold them in place. Something unseen had to be providing additional mass. Decades later, in the 1970s, Vera Rubin and her colleagues measured the rotation curves of individual galaxies. They discovered that stars far from the galactic centers were moving at nearly the same speed as stars near the center. If only visible matter were present, the outer stars should move more slowly, like the outer planets in our solar system. Instead, their speed stayed flat, implying that an unseen halo of matter surrounded each galaxy. Since then, evidence for dark matter has grown across many areas of astronomy. Gravitational lensing, where massive objects bend the path of light from more distant galaxies, shows more mass than what we can see. The cosmic microwave background, the faint radiation left over from the Big Bang, contains subtle patterns that reveal the amount of matter present in the early universe. The structure of the cosmic web, the vast network of filaments and clusters seen in simulations and observations, requires dark matter to form as it does. Every line of evidence points to the same conclusion. Most of the matter in the universe is invisible, exerting gravity but not light. The scale of this hidden weight is staggering. About 85% of the matter in the universe is dark. All the stars, planets, nebulae, and galaxies that shine are only the tip of the iceberg. The majority lies unseen, yet its gravity sculpts the cosmos. Without dark matter, galaxies would not have formed as they did. The early universe would have expanded too quickly for structures to grow. Dark matter acted as scaffolding, pulling ordinary matter into clumps that became galaxies and stars. The universe as we know it would not exist without this silent framework. Despite its importance, the nature of dark matter remains a mystery. Many candidates have been proposed. One possibility is that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact through the weak nuclear force and gravity, but not electromagnetism, making them nearly invisible. Other candidates include axions, extremely light particles predicted by some theories, or sterile neutrinos, a type of neutrino that does not interact through the weak force. Each option comes with challenges and requires experiments to test. physicists have built sensitive detectors deep underground to search for interactions between dark matter and ordinary matter. These detectors are shielded from cosmic rays and radiation, waiting for the rare moment when a dark matter particle might collide with an atomic nucleus. So far, no conclusive detections have been made. Particle accelerators like the Large Hadron Collider also search for signs of dark matter in high-energy collisions, looking for missing energy that might indicate invisible particles escaping. Again, the results are still inconclusive. The search continues, driven by the knowledge that identifying dark matter would be a breakthrough in both cosmology and particle physics. Even though we do not yet know what dark matter is, we can map its effects. Astronomers use gravitational lensing to create images of dark matter distribution in galaxy clusters. Simulations show how dark matter filaments form a cosmic web, with ordinary matter collecting along them. These maps reveal a universe where the luminous parts are only a thin frosting on top of a much larger invisible structure. It is as if the galaxies we see are lights decorating a vast unseen framework. The influence of dark matter is not limited to shaping galaxies. It may also affect their evolution. Interactions between dark matter halos and ordinary matter influence star formation rates. Collisions of galaxy clusters provide dramatic evidence, such as the Bullet Cluster, where the separation between hot gas and gravitational mass indicates that dark matter passed through largely unaffected while ordinary matter slowed. Observations like this provide some of the clearest proof that dark matter is real and distinct from ordinary matter. What makes dark matter especially fascinating in the context of power is that it does not release energy the way stars or supernovae do. It does not shine or explode. Its strength lies in its weight, in its quiet gravitational presence. Over billions of years, this presence has been decisive, gathering matter, sculpting galaxies, and building the structures that define the universe. Power here is not dramatic bursts but enduring influence, subtle yet overwhelming in scale. There is also the question of whether dark matter might reveal new physics beyond the standard model, the framework that currently describes particles and forces. The discovery of dark matter's true identity could lead to insights about symmetry, unification, and the nature of space-time itself. Some theories even suggest connections between dark matter and dark energy, though they are thought to be separate phenomena. Both remain among the biggest open questions in science. It is remarkable that something so influential remains invisible. You cannot see dark matter directly, but you move within its gravitational field every day, because our own galaxy is embedded in a dark matter halo. As Earth orbits the Sun, as the Sun orbits the centre of the Milky Way, we're carried along within an ocean of dark matter particles. Their presence is silent, but their effects are written into the very structure of the cosmos. The search for dark matter continues with persistence and creativity. New detectors, new telescopes, and new theoretical models push the boundaries of what we know. Each non-detection narrows the possibilities. Each observation of galaxies and clusters provides more clues. The answer may come from an experiment deep underground, a new particle observed in a collider, or an unexpected signal from space. Whatever the outcome, solving the riddle of dark matter will transform our understanding of the universe. When scientists measured the universe's expansion near the end of the 20th century, they expected to find that gravity was gradually slowing it down. Galaxies, stars, and clusters all exert mutual attraction, and over billions of years that pull should have been reducing the pace of expansion set in motion by the Big Bang. But when astronomers looked carefully at distant supernovae, using them as standard candles to measure how far away galaxies were, and how fast they were receding, the results came as a shock. Instead of slowing, the expansion was speeding up. Something unseen was driving galaxies apart faster and faster. This unknown cause is what we now call dark energy. Unlike dark matter, which pulls through gravity, dark energy pushes, creating a repulsive effect on cosmic scales. It is not matter at all, at least not in the conventional sense. It is a property of space itself, something built into the very fabric of the universe. Its influence grows as space expands, meaning that the more the universe stretches, the more dominant dark energy becomes. Today, dark energy makes up roughly 70% of the total energy content of the universe, outweighing dark matter and ordinary matter combined. This simplest explanation for dark energy comes from Einstein's equations of general relativity. When he first wrote them, he included a term called the cosmological constant, which acted as a kind of energy inherent in space. At the time, Einstein believed the universe was static, and he used the constant to counterbalance gravity. Later, when expansion was discovered, he thought the constant unnecessary, and reportedly called it his greatest mistake. Yet decades later, the accelerating universe suggested that a cosmological constant might indeed exist, providing a natural explanation for dark energy. In this view, every cubic meter of space contains a small amount of vacuum energy, constant and uniform. As the universe expands, more space comes into existence, and with it more vacuum energy. The result is an acceleration that grows stronger with time. If this is correct, then dark energy is simply a feature of space, always present, always pushing. But there are other possibilities. Some theories suggest that dark energy might not be constant but dynamic, driven by a field that changes over time. These models go by names like quintessence, imagining an energy field spread throughout space that influences expansion differently at different epochs. Testing these ideas requires precise measurements of how the universe has expanded across billions of years, which astronomers attempt by studying distant galaxies, supernova, and the cosmic microwave background. Whatever its nature, the influence of dark energy is profound. Without it, the universe might one day have slowed enough for gravity to reverse the expansion, pulling everything back together in a big crunch. Instead, dark energy ensures that the universe's expansion accelerates. Galaxies are being pushed apart at increasing speeds. In the far future, distant galaxies will move beyond our observable horizon, disappearing from view forever. The cosmos will become emptier, with only the nearest galaxies remaining visible, and eventually even those drifting away. This fate is sometimes described as a heat death, where stars burn out, matter decays, and expansion continues endlessly, spreading energy thinner and thinner. It is a vision of the ultimate consequence of dark energy. Not a fiery collapse, but a gradual, quiet dispersal. While gravity gathers and binds, dark energy disperses and isolates, reshaping the destiny of the universe over unimaginable timescales. The energy scale involved is difficult to comprehend. On local scales, dark energy is undetectable. It does not affect the orbit of Earth around the Sun or the structure of galaxies in any noticeable way. Gravity dominates in those realms, but across billions of light years, where space itself stretches, the effect builds. The acceleration of the cosmos is not strong compared to the forces we feel daily, yet it is relentless and universal. Over cosmic distances, even a subtle push becomes decisive. Physicists still wrestle with the mystery of why dark energy has the value it does. If it is a cosmological constant, then calculations from quantum field theory suggest it should be many orders of magnitude larger than what we observe. Perhaps the most extreme mismatch between theory and experiment in science. Why it is so small, yet not zero, is unknown. This puzzle is called the cosmological constant problem, and it remains unsolved. Some suggest that our universe may be one of many, each with different values, and we happen to exist in one where dark energy is small enough to allow galaxies and life. This idea, while speculative, highlights how deeply puzzling dark energy is. In terms of power, dark energy demonstrates something unusual. It does not produce dramatic bursts of radiation, like supernovae, nor does it release gravitational waves like merging black holes. Its power lies in its subtlety and persistence. Over billions of years, it has reshaped the cosmos, determining not only how galaxies move but how they will evolve in the future. It is a quiet dominance, spread everywhere, unstoppable by any local force. Observations continue to refine our understanding. Projects that map the distribution of galaxies across cosmic time, such as large sky surveys, provide clues about how dark energy behaves. Measurements of the cosmic microwave background show how it influenced the early universe. The coming decades may bring new instruments capable of narrowing down whether dark energy is truly constant or something more complex. Each measurement adds a piece to the puzzle, helping us understand this force that dominates everything we see. It is humbling to realize that the majority of the universe is governed by something we cannot see, touch, or fully explain. Dark matter shapes galaxies, but dark energy shapes the universe itself. Together they form about 95% of the cosmic budget, leaving only a small fraction to the ordinary matter of stars, planets, and people. We live in a universe where the most influential components are also the most mysterious. At ordinary human scales, physics feels familiar. You can see how objects fall, you can feel resistance when you push against something, you can predict how a ball will bounce or how a pendulum will swing. Even when we look into the sky, at planets orbiting stars or galaxies moving through space, the rules remain comprehensible, extended versions of the same principles. But there is a frontier where our usual ways of thinking fail. It is the boundary where the very small and the very strong meet, where gravity collides with quantum mechanics, where the known laws of physics strain under conditions that cannot be directly reached in laboratories. This frontier is called the Planck scale, and it represents the limits of power, knowledge, and measurement. The Planck scale is defined by natural units named after the physicist Max Planck, who laid the foundations of quantum theory. By combining the constants of nature, the speed of light, the gravitational constant and Planck's constant, we arrive at quantities that set ultimate boundaries. The Planck length, about 1.6 times 10 to the negative 35 meters, is the smallest scale at which space itself might have meaning. The Planck time, about 5.4 times 10 to the negative 44 seconds, is the shortest duration that can be physically significant. The Planck energy, about 10 to the power of 19 giga-electron volts, is the energy scale where quantum effects of gravity are expected to become unavoidable. These numbers are far beyond what we can directly probe, but they provide a framework for where our current theories break down. Why does this matter for understanding power in the universe? Because the Planck scale represents the ultimate test of energy density and force. At such scales, the smooth fabric of space-time described by general relativity may no longer apply. Instead, space and time might become quantized, grainy, or fluctuating, shaped by the principles of quantum mechanics. The concept of a continuous space-time might dissolve, replaced by a deeper layer of physics we do not yet understand. The Planck scale is where black holes shrink to their minimum meaningful size, where the Big Bang begins, and where the boundaries of knowledge force us to confront new ideas. Consider black holes again. If you compress matter into a region smaller than the Planck length, our current equations lose meaning. The singularity at the center of a black hole, described by general relativity, is a mathematical infinity. But infinities are signs of incomplete theories, not physical realities. At such scales, quantum gravity must take over, smoothing or replacing the singularity with something else. To know what truly lies at the core of a black hole, we would need a theory that works at the Planck scale. The same applies to the beginning of the universe. When cosmologists trace the expansion backward, they reach a point where densities and temperatures become so high that quantum effects of gravity cannot be ignored. The first fraction of a second after the Big Bang is hidden behind this barrier. To understand what happened then, whether there was a singularity, whether time itself began, whether other universes exist, we need physics that can describe the Planck era. Without it, our picture of cosmic origins remains incomplete. The energies required to probe the Planck scale directly are unimaginably beyond current technology. Particle accelerators like the Large Hadron Collider reach into the trillions of electron volts, powerful by human standards, but still 16 orders of magnitude below the Planck energy. To reach that scale with an accelerator would require a machine larger than the galaxy, which is clearly impossible. Instead, scientists look for indirect evidence. High-energy cosmic rays, gamma-ray bursts, and the radiation from black holes may all provide hints of Planck-scale physics. Gravitational waves, too, could carry imprints of phenomena from those earliest times. Each observation is a chance to catch a glimpse of a frontier we cannot otherwise reach. Some theoretical approaches attempt to describe what happens at these scales. String theory suggests that the fundamental building blocks of the universe are not particles but tiny strings vibrating at different frequencies. These strings are on the order of the Planck length, and their vibrations give rise to the particles and forces we observe. Loop quantum gravity, another approach, proposes that space itself is made of discrete loops, woven into a network that gives rise to geometry. Both theories attempt to remove the infinities of singularities and replace them with finite structures. Neither is yet confirmed, but both are motivated by the need to understand the Planck regime. In terms of power, the Planck scale represents the maximum densities and energies nature can sustain before our current physics ceases to apply. A Planck scale black hole would have a mass about equal to a mountain, compressed into a size smaller than a proton. Its evaporation through Hawking radiation would release enormous energy in a fleeting instant. Such black holes might even have formed in the early universe, if conditions allowed density fluctuations high enough. Whether they still exist, evaporated or left relics is an open question, but their possibility shows how extreme the Planck scale can be. It is also at the Planck scale that the unification of forces is expected to occur. At low energies, we see four distinct interactions: gravity, electromagnetism, the strong force, and the weak force. At higher energies, the weak and electromagnetic forces merge into the electro-weak interaction. Some theories suggest that the strong force will unify with them at even higher energies. At the Planck scale, gravity itself may join the others, producing a single fundamental force. If true, then the diversity of forces we observe today may be the result of symmetry breaking in a much more unified past. Understanding this would mean understanding the deep origin of power itself. The Planck scale is not only a boundary but a guide. It tells us where our theories must evolve. It shows us the limits of measurement, the smallest scales of space and time, the highest energies we can meaningfully describe. It reminds us that even our most successful frameworks, general relativity and quantum mechanics, are incomplete, and that the most powerful phenomena in the universe cannot be fully explained without going further. While we cannot reach the Planck scale directly, its influence stretches outward. It shapes how we think about black holes, the early universe, the unification of forces, and the nature of space-time itself. It sets the ultimate standard for what power means, not in the sense of light or explosions, but in the sense of limits. Beyond it lies the unknown, the place where physics must grow. When we imagine empty space, it is tempting to think of nothing at all, a complete absence of matter, radiation, or structure. For centuries, that was how the vacuum was understood, as emptiness, a void without content. But modern physics reveals a very different picture. What we call empty space is not empty in the deepest sense. It is alive with energy, fluctuations, and fields. The vacuum is a dynamic arena, and its properties may hold some of the greatest secrets about the universe. The concept of vacuum energy comes from quantum mechanics. According to classical physics, a system at rest with no motion and no heat should have zero energy. But quantum physics does not allow absolute stillness. Every field has fluctuations, even at its lowest possible energy state. This lowest state is called the vacuum state, and it is not truly empty but filled with restless activity. Virtual particles appear and vanish, energy fluctuates for brief moments, and fields never settle to absolute zero. This constant undercurrent is what we mean by vacuum energy. Quantum field theory, the framework that combines quantum mechanics with special relativity, describes all particles as excitations of underlying fields. The electron is an excitation of the electron field. Photons are excitations of the electromagnetic field. Quarks belong to their own fields, and so on. Even when no particles are present, the fields remain, filling all of space. The vacuum is therefore not nothing but a collection of all these fields in their ground states. Their combined energy is what we call vacuum energy. This might sound abstract, but the effects of vacuum fluctuations are measurable. One of the most famous demonstrations is the Casimir effect. If you place two metal plates extremely close together in a vacuum, they experience an attractive force. This happens because the quantum fluctuations of the electromagnetic field are restricted between the plates, allowing fewer modes of oscillation compared to outside. The imbalance produces a pressure that pushes the plates together. Though tiny, this force has been measured experimentally, proving that the vacuum is not truly empty. Vacuum energy also plays a role in particle interactions. Virtual particles, which exist fleetingly within the rules of quantum uncertainty, influence measurable quantities like the charge and mass of particles. These corrections, known as quantum loop effects, have been observed with astonishing precision. The magnetic moment of the electron, for instance, matches theoretical predictions that include vacuum fluctuations to more than 10 decimal places. The agreement between theory and experiment shows that the vacuum is not an inert backdrop, but an active participant in physics. On the cosmic scale, vacuum energy may be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If every field has a non-zero energy in its ground state, then the total vacuum energy should act like a cosmological constant, producing a repulsive effect on space-time. The problem is that calculations of vacuum energy from quantum field theory give values enormously larger than what we observe in cosmology. The discrepancy is so vast, up to 120 orders of magnitude, that it's sometimes called the worst theoretical prediction in physics. Why the observed value is so small compared to the naive calculation is one of the deepest puzzles in science. Some physicists suggest that cancellations between different fields reduce the effective vacuum energy. Others propose that new physics, perhaps linked to supersymmetry or string theory, changes the calculation. Another idea is that our universe is one of many, each with different values of vacuum energy, and we inhabit one where the value happens to allow galaxies and life. None of these explanations are proven, but all acknowledge that the vacuum is central to the mystery. The role of quantum fields extends far beyond vacuum energy. They are the foundation of everything we see and measure. The Higgs field, for example, is responsible for giving mass to fundamental particles. Without the Higgs mechanism, particles like electrons and quarks would be massless, and matter as we know it would not exist. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed this picture, showing that even the property of mass itself arises from interactions with an underlying field. The vacuum of the Higgs field is not empty but filled with a constant value across space, endowing particles with their identities. Vacuum fluctuations may also have shaped the early universe. During a period called cosmic inflation, a tiny fraction of a second after the Big Bang, quantum fluctuations in fields were stretched to cosmic scales by rapid expansion. These fluctuations became the seeds of galaxies and clusters, leaving imprints in the cosmic microwave background that we can observe today. In this sense, the large-scale structure of the universe grew out of quantum ripples in the vacuum, magnified to astronomical dimensions. Even today, the vacuum continues to influence phenomena across scales. The stability of matter depends on the interplay of quantum fields, the rates of radioactive decay, the strengths of interactions, the existence of forces, all trace back to the underlying quantum fields and their vacuum states. The apparent emptiness between stars and galaxies is therefore not a void, but a stage filled with invisible players whose quiet presence shapes everything we see. Thinking about vacuum energy also challenges our idea of power. Power often seems tied to motion, to explosions, to visible change, but the vacuum's power is subtle, everywhere at once, shaping physics not through bursts but through constants. Its influence may set the expansion of the universe, the masses of particles, the very rules of interaction. It is an invisible reservoir, steady and omnipresent, against which all activity unfolds. Despite decades of study, the true nature of vacuum energy remains elusive. Is it a fixed property of space, as the cosmological constant suggests, or is it dynamic, changing over time as quintessence models propose? Could it be tied to unknown particles or dimensions beyond our perception? Each possibility points to physics beyond our current understanding, and each has implications for the fate of the cosmos. If dark energy is constant, expansion will continue accelerating forever. If it changes, the universe's future could be very different, perhaps even reversing into collapse or tearing apart in a big rip. The vacuum holds the key to these outcomes. Experiments continue to probe the quantum vacuum. High-energy collisions test the properties of fields, precision measurements look for tiny deviations that might reveal new physics, and astronomical observations constrain the role of vacuum energy in cosmic evolution. The answers may not come quickly, but they are essential for a full picture of power in the universe. What we know already is profound. Empty space is not empty. It is filled with fields, fluctuations, and energy. The vacuum is an ocean, invisible yet real, underpinning every particle and interaction. Its presence is quiet but decisive, setting the stage for matter, forces, and the cosmos itself. When we look out into the universe, what we see is not only distance but also time. The farther away a galaxy is, the longer its light has been travelling to reach us. In that sense, every observation is a glimpse into the past. By tracing this path far enough, astronomers realise that the universe must once have been smaller, hotter, and denser. All the galaxies, all the stars, all the space itself were once concentrated into a state of extraordinary energy. That beginning is what we call the Big Bang, the first burst from which everything we know emerged. The evidence for this picture comes from multiple directions. The most immediate clue is the expansion of the universe itself. In the 1920s, Edwin Hubble and his colleagues measured the light from distant galaxies and discovered that almost all were moving away from us. Their light stretched to longer wavelengths, a phenomenon called redshift. The farther a galaxy is, the faster it recedes. This simple relationship indicates that space itself is expanding. If it is expanding now, then in the past it must have been smaller. By extrapolating backward, we reach a moment when the entire observable universe was compressed into an incredibly dense, hot state. Another line of evidence is the cosmic microwave background. In the 1960s, Arno Penzias and Robert Wilson detected a faint uniform radio signal coming from every direction in the sky. This was quickly recognised as the afterglow of the Big Bang, light that has been travelling since the universe was only a few 100,000 years old. At that time, the universe cooled enough for atoms to form, allowing photons to travel freely for the first time. Those photons, stretched by billions of years of expansion, now appear as microwaves. The cosmic microwave background is a snapshot of the infant universe, a direct relic of its earliest times. A third piece of evidence comes from the abundance of light elements. Nuclear reactions in the first few minutes after the Big Bang produced hydrogen, helium, and trace amounts of lithium. The observed ratios of these elements across the universe match the predictions of Big Bang nucleosynthesis, providing further confirmation. Together, these lines of evidence paint a consistent picture. The universe began in a hot, dense state, and has been expanding and cooling ever since. The first burst of the Big Bang is not something we can see directly. Our equations take us back to a fraction of a second after it began, but before that lies a barrier where our current physics cannot penetrate. At extremely high densities and energies, quantum effects of gravity become important, and general relativity alone no longer applies. Whether there was an initial singularity, a point of infinite density, or whether some earlier state existed remains an open question. Some theories propose that the universe began with a quantum fluctuation, others that it is part of a larger multiverse, still others that time itself may have emerged in the process. For now, we can only describe what happened after the first instance. One of the key moments in this story is inflation. According to this idea, in the first tiny fraction of a second, the universe underwent an exponential expansion, growing by an enormous factor in an unimaginably short time. This rapid stretching smoothed out irregularities and explains why the universe looks so uniform on large scales. Inflation also magnified quantum fluctuations, stretching them into seeds of cosmic structure. The galaxies, clusters, and filaments we see today can be traced back to those ripples, written into the fabric of the early universe. Evidence for inflation comes from the patterns in the cosmic microwave background, though the details are still under investigation. As the universe expanded and cooled, it passed through different eras. In the first moments, energies were so high that all forces may have been unified. As temperatures dropped, the forces separated, first gravity, then the strong force, then the electroweak force splitting into the weak and electromagnetic. This sequence of symmetry breaking shaped the behavior of particles and fields, setting the stage for the physics we know today. Quarks combined into protons and neutrons, nuclei formed in the first few minutes, atoms assembled hundreds of thousands of years later, stars and galaxies emerged hundreds of millions of years after that. From a hot plasma of particles, the universe became structured and luminous. In terms of power, the Big Bang represents the most concentrated release of energy imaginable. Every particle, every photon, every fluctuation of the vacuum was contained in that early state. The density and temperature were so extreme that no experiment on Earth can come close. The first burst was not an explosion in space, but an expansion of space itself, carrying energy outward in all directions. It is the origin of all later processes: fusion in stars, supernova, black holes, and even the quiet push of dark energy. Without it, nothing else would follow. It is striking that we can reconstruct this history at all. By studying faint signals, background radiation, and the distribution of galaxies, scientists piece together a timeline billions of years long. The earliest fractions of a second remain hidden, but much of what came after is accessible. The cosmic microwave background, for instance, preserves tiny variations in temperature that reflect density fluctuations in the early universe. These variations, only a few parts in 100,000, grew under gravity into the structures we see today. In this way, the first burst continues to echo, not only in radiation, but in the very arrangement of galaxies. Questions remain about what, if anything, came before the Big Bang. Some theories suggest a cyclical universe, where expansion and contraction alternate endlessly. Others propose that our universe budded off from a larger multiverse, one bubble among many. Still others argue that time itself began with the Big Bang, making before meaningless. These ideas remain speculative, but they remind us that the first burst is not just a scientific concept, but also a philosophical frontier. It is where physics meets questions about origins, causality, and existence itself. For our purposes, what matters is that the Big Bang represents the ultimate source of cosmic power. It set everything into motion, created the conditions for matter and energy, and continues to shape the universe's evolution. The forces we study, gravity, electromagnetism, nuclear interactions, all emerged in its aftermath. The elements we depend on, the light we see, the dark energy driving expansion, all trace back to that first moment. It is the foundation of every subsequent display of power. When people think about the end of the universe, the images that come to mind are often fiery or sudden. Explosions, collapses, cataclysms that erase everything in a single moment. But the future that many physicists consider most likely is not violent at all. It is quiet, drawn out and inevitable, the slow unwinding of all energy until nothing remains to change or move. This outcome is called the heat death of the universe, and it is one of the strangest and most profound consequences of the laws of thermodynamics. To understand this fate, it helps to return to the concept of entropy. In physics, entropy measures the number of ways a system can be arranged, or the degree of disorder within it. Over time, systems tend to evolve toward higher entropy. Heat flows from hot to cold. Energy spreads out rather than concentrating itself. This tendency is described by the second law of thermodynamics, which states that in a closed system, entropy never decreases. The universe itself is the ultimate closed system, and so its entropy must increase over time. In the early universe, entropy was low. Matter and energy were dense and uniform, with little room for disorder. As the universe expanded, structures formed, stars, galaxies, clusters, but entropy kept rising. Stars burn fuel, releasing radiation that spreads into space. Black holes form, gathering matter and locking it away, but also radiating entropy in their own way. The process continues without reversal. In the far future, after stars exhaust their fuel, entropy will reach its maximum possible value and no usable energy will remain. The timeline for this process is immense. In the next few billion years, stars like our Sun will finish burning and fade into white dwarfs, neutron stars or black holes. Larger stars will explode in supernovae, scattering elements into space. For trillions of years afterward, the smallest red dwarf stars will continue shining faintly, but eventually even they will go dark. The universe will enter an era of remnants, where only cooling embers of stars remain. Over longer timescales, white dwarfs may slowly crystallize, turning into cold, dark spheres of carbon and oxygen. Neutron stars will cool as well, radiating away their heat into space. Black holes will persist, swallowing matter and light, growing as they consume. For a time, galaxies will still exist, though dim, with stars orbiting within them. But eventually, through gravitational interaction, stars and remnants will be flung out into intergalactic space, leaving galaxies to dissolve. In this distant future, black holes dominate. They are the last great engines of energy, powering jets and accretion disks as long as material falls into them. But even they cannot last forever. According to Hawking's theory, black holes slowly emit radiation, losing mass over time. For stellar mass black holes, the evaporation process takes a timescale far longer than the current age of the universe, but it is not infinite. Eventually, even the most massive black holes will radiate away their mass and vanish in flashes of energy. After the black holes are gone, the universe enters its final phase. With no stars, no galaxies, no black holes, only thin gas and low-energy photons remain, spread uniformly across space. The temperature of the universe approaches absolute zero. No gradients of heat exist, and without gradients no processes can occur. Entropy has reached its maximum, and everything is in thermal equilibrium. This is the heat death, a state where nothing more can happen, because energy is too evenly distributed to do work. It is strange to think of the end of everything not as an event but as a condition. A silent cosmos, dark and cold, with no stars to shine, no structures to form, no possibility of complexity. The timescales involved are so long that they dwarf every human imagination. Numbers like 10 to the power of 100 years or more appear in calculations, far beyond anything we can compare to daily life. And yet, The direction of entropy makes the conclusion clear. Unless some new physics intervenes, the universe tends toward this fate. For some, the heat death feels unsettling, a story of inevitability without drama, an end without climax. But for physicists, it is the natural consequence of the laws that govern energy, the same principles that explain why your coffee cools on a table, why stars radiate, why systems spread out and decay, extend to the universe itself. It is a reminder that the laws of thermodynamics are universal, applying on the larger scales just as they do in kitchens and laboratories. There are, of course, alternative scenarios. If dark energy changes over time, the expansion of the universe might evolve differently. A stronger repulsion could lead to a big rip, where galaxies, stars, planets, and even atoms are torn apart by runaway expansion. A reversal of dark energy could cause the universe to collapse into a big crunch. Cyclic models imagine endless expansions and contractions. But in the absence of such changes, the heat death remains the simplest projection of what lies ahead. Thinking about this long fate places our current era into perspective. We live in a universe that is still young, filled with stars, galaxies, and energy flows. It is a time of activity, creativity, and change, a brief but spectacular moment in the cosmic timeline. The structures we see, the processes we study, the life that exists, are all possible because the universe is far from equilibrium. The very fact that entropy is still increasing allows for the richness we experience. Heat death is the end point of that journey, the destination once all possibilities are exhausted. Power in the context of heat death is subtle. It is not about sudden displays of energy, but about the long dominance of entropy, the quiet rule that shapes everything over time. The second law of thermodynamics may be one of the most powerful principles in nature, not because it causes explosions or collapses, but because it dictates the arrow of time itself. It tells us why the past differs from the future, why processes unfold in one direction, and why the universe must eventually settle into stillness. Even if the universe one day reaches heat death, the path there is filled with wonders. Black holes evaporating in their final moments, remnants cooling into silence, rare collisions and interactions playing out against an ever darker background. Each stage has its own displays of power, drawn out across unimaginable durations. The story does not end in a single instant, but in a long fade, a slow progression toward equilibrium. Physics has achieved extraordinary successes in explaining the universe. We have theories that describe gravity on cosmic scales, theories that describe particles and forces on quantum scales, and observations that confirm both to remarkable precision. Yet when we look closely, we find that these two pillars, general relativity and quantum mechanics, do not fit neatly together. Each works beautifully in its own domain, but at their intersection, in places like the centre of black holes or the beginning of the universe, the rules break down. To resolve this tension, scientists pursue something grander, a theory of everything, a framework that unifies all the forces and particles into a single coherent picture. The dream of unification is not new. In the 19th century, James Clerk Maxwell showed that electricity and magnetism were two aspects of the same force, electromagnetism. In the 20th century, physicists unified electromagnetism with the weak nuclear force, creating the electroweak theory, confirmed by the discovery of the W and Z bosons. The strong nuclear force is described separately, but it too may unify with the electroweak interaction at high energies, leading to what is called a grand unified theory. Beyond that, gravity remains separate, the most difficult force to bring into the fold. A true theory of everything would encompass all four forces, showing that they are different expressions of a single underlying principle. String theory is one of the leading candidates for such unification. It proposes that the fundamental building blocks of the universe are not point particles, but tiny vibrating strings. Different vibrational modes correspond to different particles. Remarkably, String theory naturally includes a particle that behaves like the graviton, the hypothetical quantum carrier of gravity. It also requires extra dimensions of space beyond the three we perceive, dimensions that may be compactified or hidden. String theory offers the possibility of reconciling quantum mechanics with gravity, though it remains unproven, with few experimental predictions accessible to current technology. Another approach is loop quantum gravity, which takes a different path. Instead of strings, it suggests that space itself is quantized, made of discrete loops woven into a network. This quantization avoids infinities at singularities and provides a framework for describing space-time at the smallest scales. Like string theory, it is mathematically elegant but difficult to test directly. Both approaches highlight the challenge of unification. The scales at which these effects matter, near the Planck length and Planck energy, are far beyond what experiments can reach. The search for a theory of everything is not just a mathematical exercise. It is motivated by specific puzzles. The information paradox of black holes, for instance, pits quantum mechanics, which insist that information is preserved, against general relativity, which seems to erase it beyond the event horizon. A unified theory should resolve this contradiction. The initial conditions of the universe, the question of what happened at the very first moment, also demand unification. Inflation, vacuum energy, and the nature of dark matter may all be tied to physics that lies beyond the standard model and general relativity. Experiments provide clues, even if indirect. Particle accelerators probe the structure of matter at higher energies, searching for deviations from the standard model that might hint at unification. Observations of the cosmic microwave background look for signatures of primordial gravitational waves, imprints of inflation that could connect to quantum gravity. Gravitational wave detectors capture signals from black hole mergers, testing general relativity under extreme conditions. Each piece of data helps narrow the options, guiding theorists toward or away from particular ideas. Some physicists suggest that unification may come not from a single grand theory but from a deeper principle we have not yet imagined. It could be a new symmetry, a new kind of geometry, or a new interpretation of quantum mechanics. Others point out that even if unification exists, it may remain forever out of experimental reach, hidden at energies too high to probe. In that case, the theory of everything would be a matter of mathematical beauty rather than empirical confirmation. This possibility raises questions about the nature of science itself. How far can we go in describing reality without direct evidence? Still, the pursuit continues, driven by the conviction that nature is coherent, that the forces and particles we see today emerged from a simpler unity in the early universe. The history of physics suggests that unification is a fruitful path. Each time forces once thought separate were brought together, new insights and discoveries followed. The next step may be the most difficult, but it could also be the most profound, revealing the underlying simplicity behind the universe's complexity. In thinking about power, the search for a theory of everything is significant because it aims to describe the ultimate sources of power. Gravity, electromagnetism, nuclear forces, all may be facets of one interaction. If we could see the universe through that lens, we might understand why the forces have the strength they do, why particles have the masses they do, why the constants of nature have their particular values. The theory of everything would not just unify equations. It would explain why the universe has the form and behavior that allow stars, galaxies, and life to exist. The quest also pushes human imagination to its limits. Extra dimensions, vibrating strings, networks of space-time, multiverses, all are ideas born from the attempt to unify. They stretch our sense of what is possible and what is real. Whether or not these specific models turn out to be correct, the very act of seeking unification expands the horizons of science. It forces us to question assumptions, to test the boundaries of knowledge, and to confront the unknown. At the same time, the search has practical consequences. Technologies developed for particle physics astronomy, and computation spill into daily life, from medical imaging to data analysis to advanced materials. The pursuit of unification drives innovation, even if the ultimate goal remains distant. In this way, the search for a theory of everything shows that even the most abstract questions can lead to tangible progress. Perhaps the most important aspect of this search is its role in framing the future. If the universe is heading toward heat death, then only a unified theory can tell us whether that fate is absolute or whether other possibilities exist. If dark energy is vacuum energy, then only quantum gravity can explain why it has the value it does. If black holes evaporate, then only unification can describe what happens to the information they contain. The answers to these questions lie at the intersection of the very large and the very small, the place where a theory of everything is needed most. And so the search continues, not with guarantees, but with determination. Each experiment, each observation, each equation is a step toward understanding. Whether the final answer comes in decades, centuries, or never, the pursuit itself is a display of intellectual power, the human drive to connect, unify, and explain. If the universe is governed by laws we strive to unify, if power can be measured in forces, energies, and structures, then what does that mean for us? Beyond physics, what role does interpretation play in how we understand the cosmos? Across this journey, we have traced many forms of power. We have seen gravity pulling on galaxies, electromagnetism weaving through matter, the nuclear forces binding and transforming particles, light carrying energy across space, and dark components shaping the universe at scales beyond sight. We have followed the life cycles of stars, the violence of supernovae, the collapse into black holes and neutron stars, and the mysteries of dark matter, dark energy, and the Planck frontier. Each of these reveals power in its own way, not always as raw strength, but often as persistence, subtlety, or inevitability. Now, having explored them one by one, it becomes natural to ask what power really means in the universe. In physics, power has a precise definition, the rate at which energy is transferred or transformed. By that measure, the sun shining on Earth, a supernova exploding, or two black holes merging are clear examples of immense power. But when we step back and look at the cosmos as a whole, power takes on wider meanings. Sometimes it is the ability of forces to shape matter into structures. Sometimes it is the persistence of laws, like entropy, setting the arrow of time. Sometimes it is the hidden frameworks, dark matter and dark energy, without which galaxies and expansion could not exist. One lesson is that power is not always loud or visible. The strong nuclear force hidden within atomic nuclei holds matter together with unmatched strength, yet you never feel it directly. The weak nuclear force, named for its apparent smallness, enables the transformations that fuel stars and produce the elements of life. Dark matter never shines, yet its gravitational pull sculpts galaxies. Dark energy works quietly, stretching space itself, gradually overwhelming everything else. These forces remind us that power can be silent, subtle, and essential, not only dramatic. Another lesson is that power is relative to scale. For us, a storm or an earthquake is powerful. For stars, fusion is powerful. For galaxies, gravity-binding clusters is powerful. At the level of the universe, the most powerful processes are the ones that set its structure and fate. The Big Bang, inflation, and cosmic expansion are expressions of power at the largest scales, while the Planck regime hints at power at the smallest, where the fabric of space-time itself is shaped. What seems absolute at one scale is only part of a larger picture at another. There is also the matter of endurance. Explosions may be bright, but they are brief. The sun, by contrast, shines steadily for billions of years. Entropy increases relentlessly over trillions of years. Dark energy's acceleration grows over cosmic timescales. In this sense, endurance itself is a kind of power. What lasts, what persists, often outweighs what flares and vanishes. The universe shows us both extremes, sudden bursts and long flows, cataclysms and quiet dominations. Both belong to its definition of power. When we reflect on meaning, we also see that power is not just what exists, but what we can perceive and understand. Light carries information, letting us reconstruct events billions of years in the past. Gravitational waves let us listen to collisions of black holes. Neutrinos whisper stories of fusion in stars and supernovae. Knowledge itself arises from these messengers, and in that sense, power includes the ability to communicate across space and time. Without such carriers, the universe would be silent to us. With them, it becomes a story we can tell. The search for a theory of everything reminds us that even our best explanations are incomplete. If power lies in unification, then the universe may be governed by a single principle still hidden from us. If power lies in diversity, then the variety of forces and particles may be the point itself. Either way, the pursuit of unification is an expression of human curiosity, a willingness to look beyond immediate appearances and ask how everything fits together. That too is a form of power, the ability of consciousness to reflect on the cosmos that created it. It is worth noticing that when we ask about the most powerful thing in the universe, the answer is not singular. Gravity, electromagnetism, nuclear forces, dark matter, dark energy, entropy, quantum fields, and the Big Bang all qualify in different senses. Each dominates in its domain, each shapes outcomes that the others cannot. Perhaps the lesson is that power is not about choosing one champion, but about recognizing interplay. The universe is not ruled by one force alone, but by a balance among many, each contributing to the whole. From our human perspective, power also connects to meaning. We live on a planet orbiting an ordinary star in a galaxy among hundreds of billions. We are small compared to stars, smaller still compared to galaxies, nearly invisible compared to the cosmos. And yet, within our smallness lies awareness. We can think about gravity and light, imagine black holes and dark energy, calculate the Planck scale, and measure the cosmic microwave background. We can ask questions that reach back to the first burst and forward to the long fate. That ability to reflect may not change the laws of physics, but it shapes how they are understood. In that way, power also includes perspective. If we return to the quiet definition, power as the rate of energy transfer, we see that everything in the universe is part of a flow. Energy moves from stars to planets, from explosions to space, from matter to radiation, from ordered states to disordered ones. Over time, these flows build complexity, fuel processes, and eventually smooth into equilibrium. We are part of this flow. Our bodies run on energy captured from sunlight through plants. Our technologies harness energy from matter. Our lives unfold against the backdrop of universal processes that began billions of years ago. The great powers of the cosmos filter down into daily existence, subtle but ever-present. In the end, power in the universe is not one thing. It is structure and collapse, silence and radiation, persistence and change. It is forces we can feel and forces we cannot. It is beginnings like the Big Bang and endings like the heat death. It is the invisible frameworks of dark matter and energy, the quiet hum of quantum fields, the bursts of stars, the pull of black holes, the slow drift of expansion. It is everything at once, woven together into a cosmos that both overwhelms and sustains. And so, as we let these thoughts settle, the question of what is most powerful does not demand a final answer. Instead, it opens into reflection. Perhaps the most powerful thing in the universe is the fact that it holds so many forms of power, each vital in its own way. Perhaps it is the laws themselves, simple and unchanging, that guide everything from atoms to galaxies. Or perhaps it is the capacity to wonder, to lie under the night sky, to listen, to imagine, to seek understanding. Whatever answer feels most compelling, it becomes part of the story, carried forward quietly like light moving through space, like energy flowing across time, like a thought finding its place among the stars. Thank you for drifting through this journey with me tonight, following the traces of energy and gravity, light and silence, beginnings and endings. If you found this space of calm exploration soothing, you can always return whenever you need rest or curiosity to guide you into sleep. If you'd like more nights filled with quiet science, you can stay connected by subscribing, liking, or simply letting the next story play when you're ready. For now, you can let your thoughts settle, let the rhythm of your breathing guide you, and let the vastness of the cosmos hold you as you rest.